right, well, thanks so much, Jim, for the warm introduction. Thank you all for being here. So I'm delighted to have the chance to give these lectures together with my colleague Kosuke and Imai, who I've learned a great deal from over the years. Let me just note that the slides that we're presenting today have been posted online on the NBER Methods Lecture website, so if you want to follow along, take notes, you can find them there. So the methods we're going to talk about today, Kosuke is going to focus on mediation analysis. I'm going to focus on surrogate indices. I want to start by way of motivation by noting that these methods are of great interest to us as social scientists, but also I think of tremendous relevance for policy questions. And just to illustrate that point concretely, I want to start by showing you an email I happened to get a week ago that illustrates the policy relevance of the questions we're going to talk about today, which was an inquiry from someone in the New York City Economic Development Corporation regarding a new workforce training program that they'd set up in the past couple of years in New York that seeks to build connections between people to help them find better jobs, motivated by a body of recent research which suggests that social capital is very important in the job search process and economic mobility more generally and so on. So I'll just read this quote to you, which I think underscores the key issues we're going to be discussing today. So Diana Franco says, we would love to gather any ideas to improve predictions we can make about the program's impacts. As you know, in government, we don't have the luxury of waiting 10 years to report solid outcomes. We need to be able to tell the program's story of impact on an ongoing basis. We are continuously innovating on how to be more efficient. So when I look at this quote, or many other similar emails that I've received, I'm sure a number of you have received, I think there are two fundamental questions that are being asked from a conceptual perspective. The first is whether we can find a way to measure impacts of new interventions that we might develop more quickly, rather than waiting to observe the long-term outcomes of interest. In this case, changes in career trajectories, for instance, emerging from this new approach to job training. Can we figure out some way, as she says, before 10 years to figure out the impacts of this program? So that's sort of a prediction problem. Can we find perhaps intermediate outcomes that are going to tell us within a year or two what we might expect to see in the long run? A more general version of that question, a variant of that question, is when we can measure a primary outcome of interest. So take a development economics context where I'm interested in measuring someone's income. It's hard to collect data on everyone's incomes, so I end up using some proxies, remotely sensed variables in the context of an application I'll talk about that relates to a paper that was presented earlier today in the econometrics session. In that case, where we can measure the primary outcome directly, are there conditions under which we can use proxies in order to make inferences about the outcome we're after, income in that example? So that's one class of questions embodied in the example that I started out with. A second class of questions is about the mechanisms that are underlying the impacts that we find with a given intervention. So if we think, based on prior work, that connections and social capital matter for finding a job, understanding why that's the case can be very helpful in figuring out how to make a program more efficient. Is it about the job referrals that you get from being connected to different people? Is it about information? If it's about one or the other of those mechanisms, maybe we can develop a cheaper program that specifically focuses on giving people relevant information or giving them certain types of job referrals. And so understanding mechanisms from that perspective is really critical for innovating to improve efficiency. And more generally, it's going to be essential to understand why a program's working, where it might work best, where we should be scaling it up, and so on. So in this lecture, we are going to be interested in understanding both of these questions. Now, what is the connection between them? Why are they combined into a single session? They both fundamentally involve the analysis of intermediate outcomes, either as predictors in the first case or as mediators in the second case. And so the goal of our lecture today is going to be to give an applied introduction to methods to answer these two classes of questions. So here's how we're going to organize the lecture. I'm going to start in the next 10 minutes or so by giving some motivating applications to give a concrete sense of the kinds of issues we're talking about, drawing on some recent examples from the economics literature. I'll then hand it over to Kosuke, who will talk for about an hour and a half on mediation analysis. And then after the break, I will talk about surrogate indices, the prediction problem that I started out with, and the modern theory that's emerged around those questions, and then finally wrap up by coming back to the applications that I start with and giving some recommendations for empirical practice going forward. So let me start with a first motivating example that's directly related to the email I showed on the first slide about network effects and peer effects and why they might matter for outcomes. So this is a nice paper by Catan, Salvanes, and Tomine that's going to come out in the American Economic Review, where they analyze the effect of having high school peers whose parents attended elite colleges. And they ask, what is the impact of having more peers who attended elite colleges on your own probability of attending an elite college? Is there a peer effect there? So their research design is one that's been widely used in the prior literature. It's to exploit finite sample random variation and cohort composition across cohorts. So just by chance, you might end up being in a cohort, because schools are not that big, you might end up being in a grade where there are more kids whose parents went to elite colleges, and I might end up being in a class where there are fewer kids whose parents went to elite colleges, and we're basically going to compare our outcomes and see if you are more likely to go to an elite college than I am. So they implement that analysis with Norwegian administrative data, and they find that a 1 standard deviation increase in the share of peers with elite educated parents in your school cohort increases the chance that you down the road go to an elite college by 2.6 percentage points. Relative to a mean of 10%, it's about a 25% increase, a pretty sizable impact of the composition of your peers on downstream outcomes. So that is an interesting finding in and of its own right. But what I think makes this paper striking and particularly valuable in the context of understanding what's going on here is that we can go beyond documenting this reduced form effect to unpack what exactly is driving this reduced form relationship. So in doing so, it's very useful to enumerate essentially the potential causal pathways that one might think about. If you think about the model for what might drive the link between the treatment variable and the ultimate outcome, in the paper they discuss a number of pathways which I think are quite intuitive, and there might be others as well, but for instance, one possibility is that when you're around a group of kids whose parents went to elite colleges, you learn more about how to apply to those colleges. Maybe there's an application effect. Another channel is that when you're around kids who are maybe very motivated, have been exposed to a lot of education and so on, you yourself start studying harder. There's a peer learning effect. There could also be channels in the opposite direction. There's a recent literature which suggests that there could be important relative rank effects, where if you're in a class with lots of other high-achieving peers, the teachers may essentially grade on a curve, and that may actually have a negative impact on your future outcomes. So unpacking which of these things is going on is extremely important, coming back to the initial policy question. If it's about applications, and we're trying to come up with a targeted intervention where, perhaps it's not possible to integrate every classroom better, maybe we can offer targeted application assistance, or maybe we can figure out how to change learning outcomes. Understanding the mechanisms here, of course, can be quite helpful. Now, let me note that this way of representing the outcomes is something you will see repeatedly in this lecture, and in and of itself, I think, is just a useful visualization tool. In the statistics literature, this is called a directed acyclic graph, or just a DAG for short. It's a representation of the causal mechanisms where the arrows show one variable influencing another. And this method of representing causal effects was popularized by Judea Pearl. It is now widely used in a number of different applications in statistics. So we will return to this kind of representation repeatedly in various contexts. So here's one example where, in the economics literature, we're interested in understanding these causal mechanisms in order to make more informed recommendations going forward. Let me give you a second example, which in some ways is even starker in thinking about why we might care about the underlying mechanisms rather than manipulating the original treatment itself. So here I'm going to draw from some work I've done with my colleagues Gaia Dossi, Matt Smith, John Manrinen, Owen Zadar, and Eric Zwick, where we analyze the determinants of returns to entrepreneurship in the United States using data from anonymized tax records. And let me start with just a simple plot that illustrates the key issue, one of the key issues we're interested in, which is to look at what your odds are of starting a highly successful firm in the United States, defined as a firm in the top 10% either by revenues or by number of employees based on subsequent corporate tax returns, versus your parents' income. So there are 100 dots here, one for each parental income percentile, and we're just plotting using panel data the probability that you go on to start a successful firm. And you can see there's a sharp upward sloping convex relationship here, such that kids born to parents in the top income decile are about 3.4 times more likely to start a large business than those born to parents in the bottom 90%. Now, once again, I think this is a case where it's even clearer why we're interested in understanding mediating mechanisms. If you think about the treatment here as being the birth lottery, do you by chance happen to be born to parents on the right side of this graph or the left side of this graph? It doesn't really make sense to think about manipulating that reduced form treatment directly. It's not obvious how you would swap kids in that birth lottery. But you might be interested in understanding, what is driving this relationship so that, maybe down the road we can figure out how to encourage more of those kids from lower income backgrounds to start firms that, perhaps might be successful down the road. So how can we think about that? Again, it's useful to use this DAG representation. We've got this initial treatment variable in some sense of parent income. We've got the ultimate outcome of interest of starting a firm. What are some pathways through which these variables might be linked? Well, one natural pathway to think about that people in the entrepreneurship literature have spent a lot of time considering is the idea that startup capital might matter. So if you have richer parents, you might have more money. You need money to start a firm. And maybe that's why kids from rich families are starting firms at higher rates. And that would have implications suggesting that maybe we want to provide tax credits or loans to people who have less resources to increase business startups, if that's the key mechanism. That's not the only possibility. Another class of possibilities related to broad literature on early childhood development and the labor economics literature is that childhood experiences or initial labor market experience, do you end up starting out in a job in the tech sector versus another sector? What kind of school did you go to? These upstream pipeline factors might end up mattering for whether you ultimately start a business. If this is what's going on, then you care about a completely different set of interventions in order to increase entrepreneurship down the road. So this is, again, a very clear case where we want to figure out what do these causal pathways look like, which of these mediating factors are more important. So before going into the methods of how we think one should go about doing this sort of analysis, I want to establish first sort of a benchmark with what I see just as an observer of the empirical literature. If you just attended Summer Institute talks over the past week, you will have noticed people tackling questions like this. So many presentations, typically first half is some sort of design-based presentation of a treatment effect, and then often the second half is some discussion of mechanisms, just trying to get at mediation. And the most common way that I think people tackle this in economics at the moment is to control for endogenous mediators. So for instance, suppose I take the question of how much of the difference in entrepreneurship rates between kids from low and high income families is explained by differences in access to capital. An intuitive, commonly used approach is to control for wealth at startup and measure how much of the raw gap in founding rates that we saw by parental income is explained by controlling for wealth. So just to show you concretely how that works in the context of this application, let's say we take this indicator for business startup that I was plotting initially and regress that on a dummy for having high income parents, which I'm going to define as parents in the top decile of the income distribution. I get a coefficient of 7.69 out of 1,000. So that's saying that kids with parents in the top 10% of the income distribution, they have a 7.69 out of 1,000 higher rate of starting a business, as we saw in that initial plot. So now, suppose we run that same OLS regression, but we add a control for the amount of wealth you have just prior to the business startup decision. You can see that that coefficient on the parents being in the top decile falls from 7.69 to 1.8. And so one interpretation of that is that in some statistical or accounting sense, wealth is accounting for 77% of the effect of parent income on entrepreneurship. So if you took the 77% number at face value, you would say wealth is clearly the most important determinant of this gap that we're seeing. And maybe tackling those differences in wealth through loans, tax credits, et cetera, is really going to change these entrepreneurship levels. Now, when you do this sort of analysis, many people implement this, but then are also somewhat suspicious of whether this is the right thing to do. I often find, perhaps you've had this experience in the context of a refereeing process. You submit a paper, you've got some set of results. One of the referees, often referee 2, will say something like, "That's all great, but You should say more about mechanisms. Have you considered controlling for some of the downstream factors? Let's get a sense of what the mediating mechanisms are. And then you do that, and then resubmit the paper, and often some other referee, or sometimes referee two themselves, as they say, well, that doesn't make any sense. This is a bad control. You're like, this analysis, is not really telling you anything. So we kind of go in circles, not totally clear, like, is this the right thing to do or not? And so the first part of this lecture, what Kosuke will discuss in a couple of minutes here, is trying to tackle that question. Under what assumptions is this very intuitive, simple approach of controlling for that endogenous mediator, to be precise, when is that actually valid? And then if that's not valid, in my sense is there are many applications where this is not, in fact, going to be a valid estimator. How can we identify the role of mediators when those assumptions fail? So that's part one of the lecture. That's the objective. The second part of the lecture, coming back to this DAG, is to, again, going to return to this example at the very end and go beyond mediation. Suppose you figured out using some method that it's, say, startup capital or initial labor market experience that's most important in driving these differences in entrepreneurship. Well, you might be interested in understanding not just how to have more entrepreneurs, but to say something about what the marginal returns of those new businesses are going to be. So suppose you figured out how we can induce more people to start businesses. Are they going to start businesses that are successful, or are they going to start businesses that end up failing? It's quite important to understand what those marginal returns look like. Now you can see that I've introduced returns as an additional outcome at the end there. Standard notation in this DAG approach is to denote by open circles things that we don't measure directly. Closed solid circles are going to be things that we do see in the data. I've put the returns with an open circle, indicating that this is not something that we see directly in the data. Why don't we see it directly? Because it takes years to measure whether a business is truly successful. We have a censoring problem, typically in panels, right? In this context, you're going to need to see somebody from early childhood all the way to, say, 10 years after they start a business. That's a very long time. You may not have that data. And so in this context, a very common heuristic practice is to predict those long-term returns, as I was saying earlier, using proxies measured at earlier stages, things like employment right after you started the firm, revenues, and so on, with the logic that maybe that's a forecast of what those later outcomes are. And so in the second part of this lecture, which I will give after Kosuke's part, we'll essentially ask the same pair of questions. Under what assumptions is that approach of scaling up short-term impacts valid? And if those assumptions fail, are there other ways that we might be able to predict long-term impacts? So that's the setup. That's what we hope to accomplish in the next couple hours. And so with that, let me turn it over to Kosuke, who will talk about mediation analysis.
Okay. Is this okay? All right. Yeah, thanks for invitation. I was a little surprised when I got email from Jim, and wasn't sure what I should do it for two reasons. One, I've never given a talk at the economics conference. And two, the causal mediation is, let's say, a controversial topic. So there are many reasons why I shouldn't do it, but I feel like I'll get to learn about this literature again, and also working with Raj. It's impossible to refuse. So here I am. Okay, so today I'm going to talk about mediation. It's going to be a lot of details of how mediation analysis work. I'm not going to be able to recommend, you should do this or that, but I'm trying to sort of cover the basis so that different approaches require different assumptions, so people can evaluate based on, depending on the application that they have. So let me get into this. So first, I'm going to try to set the stage by defining some of the key quantities that mediation analysis is typically interested in. Okay. So the starting off, it's the DAG that Raj introduced in his part. So here we have outcome Y, and the treatment T, and the mediator is M. Okay, so the mediator is the variable that we think is maybe representing the mechanism of the treatment effect. And the goal, I think the quantity of interest is really about this idea of direct effect and indirect effect. So indirect effect is basically the treatment affecting the outcome through the mediator of interest. That's your hypothesis. And the direct effect is basically everything else, right, other than the mediator of interest. So we're trying to sort of estimate these two types of effects. But there are many different ways to sort of define formally how these effects actually mean. Okay? The DAG is useful because this mediation analysis is really about the analysis of causal structure. So trying to sort of think about the sequence of the causal path. And to do that, the DAG is actually a formal way of doing it. So it looks like a little cute figure, but actually it's equivalent to the non-parametric structure equation model, which I think many economists are familiar with. And you can think of this DAG is equivalent to these two sets of equations here. So mediator is a function of the treatment and some error. And outcome is a function of the treatment and the mediator and some error. And usually these errors are assumed to be IID and removed from the DAG itself. So you don't actually put those in the DAG itself. But what I want you to know is that these are equivalent. So there's a lot of theorems about the DAG operations which has a mathematical representation. Okay, so the first way to sort of think about the direct and indirect effect is something called the control direct effect. Okay? To understand this, we have to use the potential outcomes notation. So y as a function of the treatment and the mediator. Okay, so this is the outcome that would be realized if the treatment is set to the little t and the mediator is set to the little m. Okay. So the definition of control direct effect is pretty intuitive. So you're basically changing the treatment from 0 to 1 while holding the mediator constant at the particular value m. Okay? So you can define this at the individual level, and if you average it over the population, you get average control direct effect. Okay? Now interpretation, as I said, it's basically direct effect of the treatment while holding the mediator at the particular value m. And you can also think of it as an effect of joint intervention on T and M, because at the end of the day, you're both intervening on the treatment as well as the mediator. Yeah. If M, the mediator, fully captures the treatment effect, then the control direct effect would be 0. Okay? Because the treatment itself is not having any impact on the outcome, because the mediator is fixed. Okay? You have to also be careful about this control direct effect because the value you set, the mediator value you set might matter. So depending on which value you pick, so if it's a binary mediator, you might set it to 0 or 1, but depending on which one you pick, you might have a very different estimate of the control direct effect. Okay, so the interaction effect can be an issue. Okay, next is the natural indirect effect. Okay, so this contrasts this with control direct effect. Natural indirect effect is a little bit more complicated. Okay. So here, this is the indirect effect. Okay, so this is the path going from the treatment to the mediator to the outcome. So here we are holding the treatment constant at t, but changing the mediator from the value that would be realized under control condition to the value that would be realized under the treatment condition. So this basically represents the treatment change, mediator change induced by the treatment. Okay? And again, you can represent this at the individual level or average over the population, and you can get the average natural indirect effect. Okay? So the interpretation of this is the effect of changing M on Y induced by the treatment. Okay? So the treatment changes, that shifts the mediator, and that affects the outcome. Okay, if there's a 0 treatment effect on M, so if the treatment have 0 effect whatsoever, then obviously the natural indirect effect would be 0. And similarly, if the mediator has 0 effect on the outcome, then the natural indirect effect would be 0. So a lot of people think that this sort of represents what we think of causal mechanism, because we are blocking the direct effect, the treatment to the outcome, while trying to estimate the effect of the treatment change on the outcome that travels through the mediator of interest. Okay. Again, if you have, this is a complete mediation. So if actually a mediator captures the entire treatment effect, then you can show that natural indirect effect is equal to the treatment effect. Okay? So there's no arrow, direct arrow from the treatment and to the outcome. Okay. Now, why people might be interested in natural indirect effect? Because it leads to the treatment decomposition. Okay? So the treatment decomposition, to understand this, you have to understand the counterpart, direct effect counterpart of natural indirect effect, which is the natural direct effect. So here, we are changing the treatment from 0 to 1 while holding the mediator constant. Okay? But instead of holding the mediator constant at a particular value, like in the control direct effect, here we are holding it at the natural value under certain treatment condition. Okay? So it could be under the control condition or the treatment condition. Okay? So again, we can define this at the individual level, changing the treatment from 0 to 1, holding the mediator constant at the natural value, or the population level, the average natural direct effect. Okay? So we talked about this. So this is basically like changing the treatment from 0 to 1 while holding them constant at m of t. Okay? Now, this represents all mechanism other than m. So this is kind of important because this little horizontal arrow, there could be a lot going on there. Okay? The m is the one that you care about, but there's many other mechanisms possibly. If you have a complete mediation, then natural direct effect will be 0. And if there's no mediation, the natural direct effect would be equal to the treatment effect. Okay. So the effective decomposition is that total effect of the treatment. So this is a usual sort of reduced form effect can be decomposed into the natural direct effect and natural indirect effect. Now the treatment value that you set is actually the opposite, but the decomposition works this way, and you can also think of it as if it's a binary treatment, you can add all those and then take an average, and that becomes the treatment effect. Okay, so the part of the reason I think that people are, some people are attracted to the natural direct effect, natural indirect effect, is that there's this decomposition, whereas the control direct effect doesn't really have that counterpart. Okay. All right, so not many economists do mediation analysis, so I had a hard time finding one. But I found one in Journal of Human Resources. So there, the Chen et al., the authors had the data on Taiwanese families. So they're looking at the educational attainment of the oldest child who's female. And the treatment here is whether you have a brother or sister. Okay? And in a society where the boys are more preferred by certain families, having a boy might lead to fewer siblings. Okay, so that's number of siblings is a mediator. So there could be a sort of multiple gender bias potential, and you can think of direct effect here is that having brother maybe takes away resources from a female child if the parents decided to invest more on the brother. On the other hand, there might be an indirect effect. So having a brother means that maybe the parents will stop having kids, and that will lead to a greater resources, so there might be a positive effect. Okay, so that's sort of the hypothesis. So you can sort of imagine that in this setting, maybe direct and indirect effects may have opposite signs, and they may cancel out. Okay, so you can sort of interpret the control direct effect and natural direct effect and natural indirect effect in this context. So the control direct effect would be just the effect of having brother while keeping the sibling size constant at the particular fixed value, for example, 2. Okay. Whereas the natural direct effect would be keeping the sibling size constant at the value that would be realized if the second child were a boy. Okay, so that's sort of the three quantities that I'm going to focus on. So just to summarize up to now, so the causal mechanism is really about how and why, not just whether the treatment affects outcomes, and we're trying to do that by looking at the intermediate outcome. Okay? So it's really about the understanding of causal structure. So the DAG is traditionally being used to represent these quantities. So I've introduced these three common quantities that people look at. And there's an effective composition for the natural direct and natural indirect effect, not for the control direct effect. And we can, but both of them have this like nice complete mediation, no mediation case, resulting in what we would expect. Okay. So next part is the standard sort of mediation analysis. So under what assumptions, like Raj said, the standard mediation analysis is valid. So I've tried to sort of illustrate what those assumptions are and how to understand them. Okay, so let's start with linear structural equation model because it gives us a lot of good intuition. So the simplest one would be something like this, where the mediator is linear model as a function of the treatment. I'm going to just omit the bunch of controls that you might have just for the sake of notational simplicity. And then outcome is just a linear model as a function of the treatment and a mediator. Okay? It turns out under this model, okay, I'm not talking yet about how you estimate this model, but under this model, if this model is true and if you know the parameter values, then you can show that the average control direct effect and average natural direct effect is actually identical. Okay? And actually it doesn't even depend on what value you set, M or T. Okay? No matter what those are, this is essentially the same. Okay? Natural indirect effect is a product of two coefficients. It's a treatment effect on the mediator and the mediator effect on the outcome. Okay? So that makes sense because if you change the treatment, that will change the mediator, and then that change will have an impact on the outcome. Okay, so in this case, the CDE and NDE are identical. So we don't have to worry about those differences, subtle differences. Okay. Great. Now we're going to add the interaction. Okay, so what I did is added this treatment mediator interaction. It seems a reasonable thing to do. Now the CDE is a little bit different. Now it's going to depend on what value you're going to set the mediator to because you have this interaction. And the natural direct effect is going to be also different. Now it's going to depend on which natural value you're going to pick. So it depends on this little t. Okay, so these red parts are different from what you had before. Okay, so yeah, so okay, here we go. Yeah, so now we have interaction. So now that there's a difference between the control direct effect and natural direct effect. It's going to depend on which value you pick, and the value is going to be different. Okay. Okay, so one thing I wanted to take away from this is that the interaction can be important. Treatment mediator interaction, you see later also that plays some role when you're thinking about analyzing this type of data. Okay, now let's make it one more step and make it a little bit more, even more complicated. So previously I assumed that everywhere has the same effect. Okay, so the coefficient is exactly the same for everybody. Now I want to relax that and then say, okay, there might be heterogeneity. So suppose that every coefficient can be different, take a different value for everybody. Okay? So that's why you have this little I parenthesis for each coefficient. Okay. So under this case, control direct effect actually isn't that different. The only thing that's different is that there's a little bar, upper bar here, which is basically average effect, average coefficient of everybody. Okay, so in a linear regression, we can estimate that, so it won't be a problem. Now, the natural direct effect is going to have a little bit more complication. So here we have average value, average coefficients, average across people, but we also have this product of this individual level coefficient, okay? And I'm not taking this out of the expectation because they could be correlated. Similarly, the natural indirect effect has this individual level coefficient, the product of it. And so I'm not touching it because it could be correlated. So this is maybe a problem because the heterogeneous effects could be correlated with each other. Okay? For example, like these two product expectation of these two individual level coefficient is not going to be equal to the product of two averages if they are correlated. Okay? So we can't just estimate the averages and then compute the product. It's also possible that the average effect is positive, both positive, but the average of product could be negative if these individual level coefficients are negatively correlated, right? So if you had for example, if you had a positive effect, people who have positive effect of treatment on the mediator are likely to have negative effect of mediator on the outcome, then you got the product to be, right, the average of the product to be negative. Okay. Unfortunately, so these averages we can identify them under exogeneity, but these are fundamentally unidentifiable because we don't really observe individual level coefficients or individual level treatment effect. Okay, so this I'm trying to illustrate that heterogeneity may play a role here. Right? If we assume homogeneity, things might be nice, and if we assume no interaction, maybe we can just run regression and go home. But with the interaction and heterogeneity, things can get complicated. So this sort of motivates a little bit more fundamental understanding of non-parametric identification. So let's not sort of make any assumptions about the model and think about what are the assumptions really we need in order to identify these things. Okay. All right. So let's first think about the identification of control direct effect. Okay. So here we have a DAG. I just added X, which is a pre-treatment confounders, which may affect treatment mediator outcome. And we are interested in control direct effect, is interested in this red arrow. Okay? The assumptions here is pretty standard. Okay? So the treatment is as if random given X. So it's independent of all potential outcomes, all potential mediator values. And the mediator is conditioning on the pre-treatment covariates, and the treatment is independent of the potential outcomes where the M may take a different value. Okay? And then we have overlap assumption that every treatment value and mediator value is right, has at least have some chance of being realized given pre-treatment values. Okay? So this is sort of standard exogeneity assumption. Okay? And in that case, we can just run regression. Okay? So we can just run regression, estimate the regression of Y on T and M on X, hold M constant, change the treatment 0 to 1, and try to estimate the control direct effect. Okay? So under this sort of exogeneity assumption, control direct effect we can identify in a usual way. Now, what about the natural direct effect and the indirect effect? Okay, so here things are a little bit more subtle. Okay? So now this is just an assumption that I took from the previous slide. There's a slight subtlety there where I was conditioning on the treatment equals set T, and when I talk about the conditional independence of the mediator and the potential outcome, I was also conditioning picking the same T. Okay? So treatment has been realized, and the mediator is being assigned. Mediator is assigned in such a way that it's conditionally independent of the potential outcome with different value of M. Okay? But the same T, because the treatment has been realized. Okay? Now, this M, you can also write it as M of T, because the treatment is conditioned as T. Okay? Now, in order to identify natural direct and natural indirect effect, we have to strengthen this assumption with something called the cross-world independence. Okay? The only difference is this little tilde. Right? So what this means is that you need to consider not only the conditional independence of mediator with potential outcome with different M given the same T that's been realized, you also need to consider the counterfactual world if the treatment were different. Okay? Some people's brain might be hurting. But, so this is, well, this assumption may be controversial in a couple ways. Okay? You can think of it as every M at the beginning of the study has a bunch of different potential outcomes depending on what the treatment is going to be and what the mediator is going to be. And the way that the mediator is being assigned down the road is independent of all those attributes. Okay? So that's one reason. But it's still you're considering the counterfactual order, what could have happened in the treatment. Okay? But this conditional independence is important. So at the very sort of accounting level, you're imposing additional conditional independence, right? So instead of just looking at the potential outcome at the t, you're also considering different t. Okay? But it turns out, for now I'm going to say that's what the assumption is required, but it turns out that has an important implication. Okay? And I'll come back to this. Okay. Now, once you make this assumption, the cross-word independence, conditional independence, then you can identify the natural direct effect and natural indirect effect in the usual way. Okay? So what you can do for the natural direct effect is you change the t from 0 to 1, so you fit the regression, you estimate this conditional expectation function, and when you set the mediator, you model that under the treatment conditions. So you have to model mediator under each treatment status, and then basically impute that into this model. So this sort of fits exactly how the definition looks like, right? Because you're going to be inserting M of t. Okay, and same thing with the natural indirect effect. Here, we're going to change the M of 1. We're going to model both M of 1, M of 0, and then put that in and take a difference. Okay. Now, why is the natural indirect effect and natural direct effect is different from control direct effect in terms of identification when you just add the little t prime instead of t? Okay. It's actually easy to think about that if you think about just an experiment. Okay. So suppose you run 2 experiments. One is you randomize the treatment and you just observe mediator and the outcome and you record that. The second experiment, you separate sample, you randomize T and M, and then you observe Y. Okay, so suppose you run those 2 experiments. What you can learn is the distribution of M of T, as well as distribution of Y of T when the M is realized under that value, treatment value. That's sort of, these are 2 quantities you get to learn from the first experiment. And from the second experiment, you get to learn this potential outcome distribution because you set the treatment and mediator randomly to a particular value. Okay? Now, this obviously identifies the control direct effect because we got this distribution, so we just need to take expectation and set the treatment to 0, 1, holding M constant. Okay? But this doesn't identify natural direct effect and natural indirect effect because for that, we need something different. This M of t has to be M of t prime. Okay. So randomization of M can't really break the natural value of M, t, and yt prime M. So you can do partial identification, but it turns out that you can show that the sharp bounds without any additional assumption always contain 0. Okay, so the sign of the natural direct effect and natural indirect effect is not identifiable. And I'll come back to some of these issues later when we talk about the partial identification issues. Okay, so what kind of experiment do we need ideally to do natural direct effect and natural indirect effect? Maybe something like what we can think of like crossover design. So crossover design is like a 2-stage experiment on the same sample. In the first stage, we're going to randomize the treatment and observe mediator and outcome, just like we did in this one experiment here. But in the second stage, you're going to use the same sample, and for the people who got the treatment, they will be assigned to the control. And people who got the control condition in the first stage will be assigned to the treatment. Okay? While also intervening on the mediator at the value that you observe in the first stage. Okay, so that's really what you need to do in order to observe these quantities. So from the first one, we get to observe this and this. Like we get to observe what would be the mediator for a particular person, the treatment condition T, and then the outcome. And then the second one, we're going to set the treatment to the opposite condition, but the whole mediator at the same, the value that you observed in the first stage. Okay, so this is what you really need in order to point identify natural direct effect and indirect effect. That's why the standard sort of experiment would not be sufficient. Okay, so obviously in this kind of experiment, you have to assume like there's no carryover effect, right? So the only thing that matters is each experiment is separate. The previous experiment is not really affecting the second experiment, even if they are on the same sample. Okay, so that sort of gives a sense of like control direct effect. See, this is much easier to identify compared to the natural direct effect and natural indirect effect. Even though the identification assumption, if you just look at the math, it's just a very slight difference. Okay. All right. There's the other way of identifying these effects, and I talked about the interaction is being important, and it's actually, we can also assume no interaction effect and identify these effects, okay? What's important though is that the assumption has to be at the individual level, okay? Not on the average. Okay, so here, we are saying the effect of the treatment when the mediator is whole constant at a particular value of m is the same, regardless of what value of the mediator you pick. Okay? Under this assumption, the natural direct effect and control direct effect is actually identical. Okay? So once you are able to identify control direct effect, natural direct effect is identified. If you subtract that from the average treatment effect, then you get the natural indirect effect. Okay? So obviously we can test this implication, but one thing to remember is that this is an individual level assumption, and what I'm writing here is that testing the group level no interaction effect conditional on the covariance. So it's a testable implication, but it's not the direct test of the, this is just the individual effect, level effect is not observable. So the only thing you can do is to really look at the group level test. Okay. So, if you're willing to make these type of assumptions, maybe perhaps like conditioning on many covariates, the homogeneous group, but without sort of this kind of strong assumptions, natural direct effect and natural indirect effect is difficult to point identify. Okay. Yeah, we talked about the estimation, and so I'm going to just go very quickly here. So we basically, once, if you're willing to assume the cross-word counterfactual, you can basically predict given each treatment value and predict outcome by first setting the treatment to a particular value and the mediator to a natural value of interest. So you can basically estimate all these things. Basically, you can impute these in this identification formula. Okay? So it's essentially fitting the regression of y given m on t, and m given t and x, and then imputing m of 1, m of 0 to calculate these effects. Okay. Yeah, and natural direct effect is also. So this is sort of standard mediation analysis one might do, and the linear case, you saw that formula that I showed you. Okay. There are some weighting methods. I'm not going to go too much into detail of the estimation, but I just want to mention that instead of just running regressions, you can also do weighting. Okay, so here, there are different weighting formulas. So this is the type of quantity you want to estimate. So it's the average of potential outcome. Treatment is set to little t. But the mediator is set to the different value of the treatment status. Okay? So one way to do this by weighting is to first estimate the conditional expectation function. So y given m on t and x. And because we want to set the treatment to little t, we're going to look at the conditional expectation function when the t equals little t. Okay? Now, m needs to be m of t prime. Okay? So we take the observation that it's actually the t equal t prime, and then do the weighting to get this quantity. Okay? So that's one way. Another way is to do double weighting. So you can think about outcome weighted by the inverse probability of treatment, assignment, and the ratio of the mediator ratio, okay? Under the t equal t and t equal t prime. So what we are observing is when the t equal t, so you do inverse weighting, but we need to get to the mt prime, so we multiply by the density of mediator and the t prime so that the values of mediator that's likely under t prime will be upweighted relative to the value that will be realized under the treatment. Okay? Now, if you use the Bayes rule, you can get the same formula becomes something like this. And this is nice because it's all modeling the treatment. Okay, so sometimes the mediator is high dimensional. So you might have multiple mediators. In those cases, modeling these might be a little awkward or difficult. Whereas this expression, just using the Bayes rule here, is all about predicting the treatment. So if the treatment is binary, that's much easier. It's much easier than the multiple mediator modeling all at the same time. But what's funny is that the treatment is regressed on mediator and x in this case. Okay, so, but that comes from the Bayes rule. Okay, so there's a lot of literature in this sort of estimation problem. So there's multiply robust, same parametric estimator leveraging this type of representation. And I think there's even double machine learning if people want to use the machine learning techniques. Okay, so this is all under the assumption of this no confounding, no unobserved confounding cross-word independence. So obviously those assumptions are very, very strong. Even the experiment cannot recover it. So the sensitivity analysis is really, really important. Okay? So I think I've seen a lot of sensitivity analysis papers starting to appear in econometrics as well. But you can imagine that when the assumptions are untestable or unverifiable, it's important to examine the robustness of empirical findings to their potential violation. So the question here is how large a departure from the key identification assumption must occur for the conclusion to no longer hold. Okay. Now the most controversial assumption is this second part, this cross-word counterfactual assumption here. So question is, what would happen if this independence is actually not true? How do we know what estimates you might get? Okay. So let's go back to the linear structure equation model. It doesn't have to be linear. You can make things more complicated, but I'm going to just keep it simple here. So suppose that in the error term, we had this unobserved confounder, ui, and that unobserved confounder also appears in the error term of the mediator. Okay, so this is the sort of standard omitted variable bias where these two things the errors get correlated because there's this unobserved confounders, both affecting the mediator and the outcome. Okay? And you have coefficients lambda in front of it. Okay? So how much does this unobserved confounder have to matter in order for your results to go away? Okay? So that's the question. So what the parameterization I found it useful is R square, using R square. Okay? So there's sort of two ways to do it. One is to think about how much this unobserved confounder, the variance of that is, how big is that relative to the entire error term. So in the error term, how much of that is actually unobserved confounder in terms of the variance. So it's a ratio of the variance. Okay. Another one is, instead of looking at the error term, you can also look at the original mediator variance. So how big the unobserved confounder has to be in terms of the explaining the original variance of the mediator or the outcome for the results to go away. Okay? It turns out, in order to do sensitivity analysis in this setting, you also have to know the direction of the effects. Okay? So you have to know the sign of these two equations. Okay? So these two lambdas that I had. So if you remember this sign of that. Okay? So this sign, it's 1 if it's the same direction, if -1 if opposite direction. So if this unobserved confounder affects the outcome and the mediator in the same direction or the opposite direction. Okay? Once we specify all these parameters, then we can calculate the effects. Okay? So here, I'm putting a contour plot. On the left, I have the case where the effects are opposite, and the case on the right, I have the case where the effects direction is the same. Okay? And on the upper half, I have, in terms of the variance, proportion of variance relative to the variance of the error term, the entire error term. And the bottom, I have in terms of original variance, the variance of the original variable, mediator, and the outcome. X-axis is the mediator, y-axis is the outcome. Okay? So if you assume the cross-walled independence, it's right here. Okay? There's no unobserved confounder. So the effect is 0 and 0. When R squared is 0, both 0. So it's, in this case, it's like a -0.5 or something like that. Okay? As you increase the amount of confounding in these directions, the effect changes. So you can sort of see that the effects become more and more negative in this case. Yeah? If the signs direction of the effects are the same, then actually effects start from here, and actually at some point it flips. So if you had like 60% of original error variance in the mediator equation is being explained by the unobserved confounder, and also 60% of original error term in the outcome equation being explained by the unobserved confounder, it might become the positive effect instead of the negative effect that you reported when you assume there's no unobserved confounding. Okay, so this kind of plot can tell you how much, you can sort of quantify how much this unobserved confounder has to matter in order for your results to have different signs and all that. If you do it in terms of original variance, then it's bounded because there's some treatment and other variables are in there already explaining some of the variances, so it's all bounded. And so you only need to look at these areas. So this is sort of the sensitivity analysis. Now, people who don't like sensitivity analysis always said, well, okay, you can tell me how sensitive you are, but you don't know what the truth is. Like, come on. Well, that's what the sensitivity analysis, the limitation of sensitivity analysis. But at least you can quantify what that effect size might be. Okay. All right, so just going back to the same application. So the authors did some standard analysis in that paper. Although it was buried in the appendix. It was discussed in the main text, but the results were actually in the appendix, which is kind of interesting. So I had to look through the appendix to find out the effects. Okay, so this is the model they fit. So it was the interaction here. There's an interaction term here. The outcome is a universal admission, so it's a binary variable. The treatment is the second child is a boy, and the mediator is the sibling size is, they have different operationalization, but the one I'm going to show you is whether they have additional child after the second child. Okay. So here's the estimates, and it's kind of precisely estimated, but it's tiny. Okay. So this is like, if you think about this as binary, so it's like less than 1 percentage point change. The average effect is essentially 0. The signs are sort of in the expected direction in the sense that the direct effect is negative. So there is, that's sort of if the female child is being biased against, it's negative effect, but the indirect effect is positive. So having the male, having brother may lead to a smaller sibling size, and that might free up some of the resources. Okay. And I'll show you some other estimates under alternative methods a little later. So just remember that effects are tiny. They also fit, actually I can discuss this in the main text, but the results are all in the appendix, as a random coefficient model, which I thought was very interesting because I told you that in the linear model presentation, I talked about heterogeneity. So one way to address heterogeneity is to do a random coefficient model. Obviously, this type of model assumes a distribution of the effects. So they put the normal prior on the random effect. So they do some address, they do some, they do consider some heterogeneity here. You can do sensitivity analysis with this type of random coefficient model without making some of those assumptions, but yeah, so that's something that I was impressed to see the authors doing that. Okay, so just to take away of the standard analysis that people often do, so there are two key assumptions beyond usual exogeneity. In the linear structural equation model world, there's a homogeneous effect and no interaction. So these two things actually seems innocuous, but it actually comes and bite you when you do mediation analysis. Okay. Under these assumptions, everything is simplified. But once those assumptions are relaxed, there are subtle issues that I just discussed in terms of both identification, but also that control direct effects and natural direct effects become very, very different. Okay. I showed you some sort of basic non-parametric identification analysis. The control direct effect is identifiable under standard exogeneity assumptions, but the natural direct effect and indirect effect requires this cross-world independence. Okay. If you're willing to assume no individual level interaction, then you're back to the simpler world where you can treat everything as essentially the same. Okay. So the fundamentally, I think when M is randomized, you're basically setting the mediator to a particular value. So that doesn't really tell you anything about natural value. And yet, often the causal mechanism, people care about natural value. So that's really the tension. So the experimental intervention is an effective intervention. But natural direct indirect effect is really talking about how treatment induces the change in the mediator. So in this type of setting, sensitivity analysis is very, very important. Okay. Now we got sort of covered the basics of the mediation analysis. I want to talk about how we might cope identification difficulties. Now, I try to sort of think through, some of the methods that's proposed in the literature. Each one has its own assumptions or subtlety and difficulties, but I'm hoping to give you some sense of what kind of strategies out there. Okay, and of course, you're all economists, so why not instrument? So the natural thing you might want to do is you got the problem of mediator endogeneity, so why don't you find the instrument? Okay, so here's a Z instrument that's affecting the mediator. Now we're going to allow the unobserved confounder. So in the DAG, if you see the dotted arc, that means that there's an unobserved confounder there, affecting both the mediator and the outcome. Okay. So now the mediator is a function of the treatment and the instrument. We can make an exclusion restriction assumption, the usual, where outcome is going to depend on Z only through treatment and mediator. Okay, so there's no direct arrow going there. So we can represent this DAG using a non-parametric structural equation model. And Y is a function of M and T, and M is now a function of T and Z. So you have this instrument. And we're going to allow now that there might be a dependence in the error term. right? So previously, we just ignored and hoped that there's no correlation there. Okay. So this is actually, in econometrics, I think people call a triangular system. I'm hoping that's terminology is right. And, a lot of smart people figured out how to estimate this type of equations. So I think the paper I found most sort of close to this is the Giro and Newey's paper about I think exactly this setup using a control function approach. Okay? So if M and Z are continuous, we can use the control function approach. What is that? So again, I'm not sure if I should be lecturing about this, but so we're going to assume that the instrument is independent of these error terms. Yeah? And then there's this monotonicity thing, right? So there's this duality between like rate approach and latent index model thing. Many of you probably know. So what this says is that condition on the T and Z, this error term is monotonic, right? Monotonic relationship between M and this error term. Okay? So you can think of it as like a scalar, it's sort of additive error term, scalar error term. Okay? Once if you assume this, they show, in engineering, show that you can have this control function. What is control function? If you throw that in a regression, the endogeneity is solved, right? That's the magic function, the control function. And the control function in this case is a conditional distribution function. So M given T and Z, and which is basically the distribution function of error term. Okay? So that sounds super complicated, but if you think about control function approach to two-stage least squares, what do? We regress Y on M and T and the first stage residual, right? Because the first stage residual is a control function. Okay. So in the linear case, that's an alternative way of doing two-stage least squares, and that regenerizes in this non-parametric setup. Okay. So there's a paper by two economists who also consider this type of approach when the treatment is also endogenous, and you have to find another instrument for the treatment. Okay, so it turns out this application, these authors did the IV analysis. So let's see how they did it. So their instrument in their context is having twins at the second birth. So the second birth is the twin. Okay? So if you think that's random, then we can think of that as an instrument. Okay? So all they did is the mediator now has a mediator equation has a Z, and actually they also included the interaction between T and Z. Okay? So what are the assumptions? Well, it has exogenous instruments, so having the twin is random, conditional on X. Obviously, having twin means more siblings, so it's right. Got one more at least. Okay, all right. If I weren't videotaped, I'll give a funny story, but I should keep going. Okay, so the exclusion restriction basically says that having twin affects the outcome only through the sibling size. Maybe not. Yeah? Okay, so when you do this by just the two-stage least squares, you get this result. So this is the previous results I showed you using the standard analysis, and this is the IV analysis. So in the IV analysis, actually the effects are a little bit bigger. So it's 2 percentage point increase, or decrease, sorry, natural direct effect in the college admission. And the indirect effect is about the same. So what's interesting is that they're sort of, they have different opposite signs, and so the average treatment effect is essentially 0, but these two are quite different. Okay? And when they did the control direct effect, they controlled it at the average value of M. And that one is not statistically significant, it's pretty small. But the natural direct effect and natural indirect effect is sort of consistent with what they were expecting. Okay, so that's sort of the one approach, like instrumental variable. approach. Okay. Other approach is something we can call complete mediation analysis. So in statistics, if you don't want to make assumption, but you still want to use the assumption, one way to get away is to do a hypothesis test. And then you say, isn't that assumption interesting? Let's test. Okay? Because in the statistical hypothesis test, you get to pick a null hypothesis. And you get to assume that's true. Right? So that seems a golden opportunity for people who are interested in mediation. Okay? So suppose we want to test complete mediation. That is, the mediator that I got is perfect. It explains all the treatment effect. Okay? So here, I'm assuming that treatment affects the outcome only through M. Okay? Under this null, we can do the test. So here's a DAG. That's how it looks like. The assumption is no unobserved confounding between T and Y. So if you see, there's no arc, direct arc between T and Y. Okay, T and Y can be correlated, but only through these two arcs. So you could have unobserved confounding between T and M, and you could also have unobserved confounding between M and Y. You just can't have unobserved confounding between T and Y. Okay? This is actually not that bad because if I randomize T, then I don't have to worry about the unobserved confounding. Okay? So actually, I can use this in the randomized experiment. And also, M can be multivariate. Okay? So if this DAG is actually true, then we can do conditional independence test. Okay? Because once I condition M and X, then the T and Y are independent. Okay? So and we know how to do this. There are a bunch of different ways of doing it. One way is to do regression-based tests. So you have to condition M and X, so you might purge those effects and get the residual, and then the residual should be independent. Okay? Or there's other fancier tests, like kernel-based tests. There's also a paper, I think, this morning that talks about this condition, complete mediation analysis, where they look at basically the same test, slightly different way of writing, but checking the treatment condition is independent of Y and a particular value of M. Okay? So it's all, I think, the same idea of, okay, we have all these assumptions that we don't believe. Can we do anything about it? Well, maybe if we collect a lot of mediators that we think it matters, and we can do this test. Now, you have to be careful about, failure to reject the null is not the endorsement of the null, so you have to be sufficiently powered to use this kind of test. But that's pretty promising. Okay? And in the randomized experiment, especially, we know that this assumption is satisfied. Okay, so that's good. This is a test of complete mediation. If you are in observational studies, then there could be unobserved confounding between T and Y. So, the rejection of the null may be because of that. We don't know what the reason if you reject the null. Right? Okay. Now, if you don't like any of this, there's something called implicit mediation. Yeah? What if we want to avoid the untestable assumption at all costs? What can we infer from average treatment effect on a mediator, well identified in the randomized experiment, average treatment effect on the outcome, well identified, randomized experiment, without such assumptions? Okay? So people have talked about this because they realize the assumptions are strong, they don't want to assume it, and can we do something about it? Okay? So this is a table from Bullock and Green in, I think, psychological science or something like that. And they have this table. This is implicit mediation. So X is a treatment here. X affects M and Y. Inference, M may be a mediator. Reason is that X appears to influence M, and has effects, seems to coincide with a change in Y, as would be expected if M were a mediator. Okay, so that's inference. It's rather informal inference, what it is. The treatment affects mediator, but not Y. Mediator appears not to be a mediator. M appears not to be a mediator. Although treatment affects M, this effect seems not to have any consequences for Y. Okay? So this sort of like, I mean, you might be thinking about this as like, oh, like this is too fuzzy. But we do this all the time. Like if you read a lot of papers, I mean, people may not, put it in a table, but like in the discussion, there's often of this type. Okay? So it's important to know, like, is that valid? Okay. So we can do some kind of simple identification analysis of this kind of implicit mediation. So the question is, does average treatment effect on mediator equals 0 imply natural indirect effect equals 0 or natural direct effect not 0? Does knowing the sign, how the treatment affects the mediator and treatment affects the outcome, does that say anything about the sign of the natural indirect effect? Okay? Unfortunately, the answer is no. Okay? Even the no assumption bounds from the parallel experiment design, where you can actually have two experiments, one where the T is randomized and T and M is randomized, we know that the bounds contains the 0. Okay? So I think none of that inference in the previous table is actually valid without additional assumptions. You can sort of get a little bit better intuition by the following decomposition, which I find it to be quite helpful. So if you think about natural indirect effect in the binary mediator case, okay, so in the binary mediator case, you can imagine there are compliers, there's people who are, mediator is equal to 1 only when the treatment is received, and defier would be the opposite, and then always taker and never takers who is not affected at all by the treatment. Okay? So if the treatment doesn't affect the mediator, then those people, natural indirect effect is 0. Okay? So the only people who matter is the compliers who are affected by the mediator and the defier who is affected by mediator in the opposite direction. Okay? So that's why we have this negative sign, because it's opposite direction. Defier and the compliers are affected by the mediator in the opposite direction. Okay? And these little p's are the proportion of compliers and proportion of defiers. So you can decompose the natural indirect effect into these different types. Okay? And we know that if you have no effect on mediator, those effects are 0. So you end up with these two subgroup effects. And obviously, like, we have no way of knowing this, because you're trying to get effect of mediator from 0 to 1 when you control for T. But in the standard case, the mediator is endogenous. So we have no way of identifying this. And also, we have no way of knowing who is a complier, who is a defier. So this is sort of gives you a reason why there's a very little, if this could go any direction in terms of natural indirect effect. Now, if we assume cross-word independence, then these M's are independent of the potential outcomes. Remember that's independence. Okay? So then we can drop this conditioning. The defier and complier doesn't matter. Okay? Then once you do that, or you can think of this as a homogeneity assumption. Like compliers and defiers have the same effect of mediator on the outcome. Once you do that, then you get usual product rule, okay? Which is the average treatment effect of mediator on the outcome multiplied by average treatment effect on the mediator. So that's the usual product rule of the standard mediation analysis. So I found this type of sort of, again, the heterogeneity matters, and cross-word assumption basically removes that heterogeneity. Okay. All right. We can also think about monotonicity. How are we doing with my time? 20? 15? Okay. Yeah. So some of these analysis is also in the Blackwell paper and Quan Roth paper. Suppose we assume monotonicity, so let's get rid of defiers. So we are left with the compliers. Maybe we can do something. Okay? But it turns out even in that case, there's a typo here, this should be minimum. Even in that case, the natural indirect effect, the sign is not identified. So a lot of these sort of this informal discussion that goes on in the implicit mediation, I don't think is really valid. This analysis shows. Okay, so basically there are two fundamental difficulties. One is the effect heterogeneity. Everyone could have different effect. And it's the endogeneity of mediators. So because you're not able to assume exogeneity of the mediator, that those two things makes things very difficult for the natural direct and indirect effect. Okay. All right, so just takeaway. The first thing I talked about is the instrumental variable approach. That seems a natural way of addressing the endogeneity problem. As long as the instrument is exogenous and exclusion restriction holds, that approach seems to be a good, reasonable solution. And non-parametric estimation is, I think, in theory possible. In practice, the conditional distribution function estimation is probably a little difficult if the covariates are high dimensional in particular. Okay, but there are tools out there that tries to address this. Complete mediation is a hypothesis testing approach. I think it's, if you like cleaner way, maybe this is the way, one way to do it. No need to really assume exogeneity of mediator. You can allow unobserved confounders. And no unobserved confounding between T and Y needs to be assumed, but in our CT, this is satisfied. Okay. And the implicit mediation is attempt to sidestep assumptions, like from the sort of methodologist point of view, that's always a bad move. You can never escape from assumptions. Okay, so in this case, it's pretty bad. It's not informative even about the signs of these effects. Okay, and even if you assume the treatment only affects the mediator in the one direction, even that is not going to really be sufficient. Okay. Okay. One last part is the even more complicated case, mediation analysis under post-treatment confounding. Okay, so here I'm considering the situation where there is a post-treatment confounding. So far, I only had this X. But now I have this confounder that's affecting both the mediator and the outcome, but also affected by the treatment. Okay, so we had this intermediate outcome, but between the treatment and the intermediate outcome, there's another intermediate outcome. Okay, so far we sort of conveniently ignore this, but you can imagine that could exist. Okay. All right. So now, instead of just conditioning on the treatment and X, we also have to condition on this post-treatment confounder. Okay. This is about control direct effect. Okay. Now, one be tempted to just simply control for this B. Okay. But that's invalid. I think that's something logical bad control. Okay? So this control is affected by the treatment, so you can't just add the V in the regression and then check the coefficient on T while fixing the mediator constant. Okay? So this is not equal. So this is known as post-treatment bias. We have to actually model V given T and X because the treatment affects the V. So we need to account for when you change the treatment and then see what happens to the outcome, you need to account for the fact that the V might also change. Okay. But usually this is a nightmare because the V could be high dimensional, and there's a lot of modeling that you have to do. Okay. So this directly modeling is usually not a good idea. Okay. So what most people do is something called marginal structural model. So you basically marginalize this V out, okay, by weighting strategy. Okay. So here, basically, in order to get this marginal mean for the control directed effect, you have IPW for the treatment and then IPW for the mediator, given the treatment and then the post-treatment confounder. And you use that Y to outcome weight by these weights. Okay. So this is a much easier strategy, especially when the V is high dimensional, because this type of model can be difficult to construct. Okay. Okay. What about the natural direct effect and natural indirect effect in this setting? So this one has an actual fundamental difficulty. Turns out the identification assumption is not going to be satisfied even with the observed post-treatment confounding. So the reason is actually you can see relatively easily by, again, thinking about this non-parametric structural equation model. So here we have the post-treatment confounder, V, which is a function of T, and M is now a function of TMV, and Y is a function of MVT. Okay? That's just this DAG that I had. So this DAG is equivalent to that 3 equations. Okay? Why does the cross-word independence does not hold? You can see this by thinking about V1 and the V0 is actually correlated because it has the same error term. Yeah? So we got the same error term, so these are correlated. Okay? And because the outcome is a function of V, even if you set the treatment to the opposite side for the mediator and the outcome, you still have these V's inside of it, so they're going to be correlated. Okay? So this tells you that when you have a post-treatment confounding, that cross-word counterfactual cross-word independence assumption you're hoping to hold is not going to hold. Okay? So what is the implication of that? I think one is that it gets more and more difficult to unpack the mechanism as the mediator becomes far away from the treatment. So if there's a lot of things happening between the treatment and the mediator, then there's this possibility of post-treatment confounding, which makes it difficult. Okay? So just conditioning TMV doesn't really solve this problem. So what people do? Well, people do the following. Okay? People change the quantity of interest. Okay? So here, I have the same exact DAG, except I promise this is the last DAG. I call it M1 and M2 instead of V and M, but it's the same thing. Okay? Okay, so this is same exact setting. There are different path-specific effects. Okay? There are 4 paths. T to Y, that's direct effect. T to M1 and Y. T to M2 and Y. And then T to M1 and M2 and Y. Yeah? What they do is they focus on combined effect. Combined effect is the treatment effect on the outcome, everything that goes through M1. So there are 2 of these. So T M1 to Y and T M1 M2 and Y. Okay? Now we know how to identify this combined effect. That's just now your standard mediation problem, because this is the first mediator. So there's no post-treatment confounder under this setup. Yeah? So we can actually we cannot identify each one separately, but we can identify this combined effect together under the cross-word independence assumption. Okay? So they basically do this, and this is a sort of generalized version of assumption. But what's important is once we do this, we can basically put it into three pieces: the direct effect, and this combined effect, yeah, and then the T to M2 and Y. Okay? So under the cross-forward assumption, the generalized cross-forward assumption, independence assumption, we can estimate the effect going through just M2, okay? Not the one that goes through M1, M2, Y. Okay? So that's sort of how people try to get around this post-treatment confounding problem in the sort of standard mediation framework. Okay. Finally, there are other effects people are interested in. And I'm not going to go too much into detail, but I'll just mention this because recently people have been looking at this quite a bit. So another way is to, again, like change the quantitative interest. So the problem was that natural value can be correlated with the potential outcome. So here, what people do is to think about basically independent draw from some distribution. So let's think about interventional distribution that independently generates this mediator, natural mediator value. Okay? So this is a definition. So with abusive notation, we're saying this is a indirect effects. So set the treatment constant and change the distribution of mediator from the one that would be generated under the treatment condition to the one generated under the control condition. Okay, so this is just changing the distribution, not changing each individual natural value. Okay? But by considering this, you basically makes it just independent, like because you're assuming the interventional distribution is an independent draw from this distribution. Okay? So you can define the average. And what's nice about that is it's sort of similar to natural independent effect, natural indirect effect and direct effect, except it's a distribution. And it's only a function of the control direct effects. So whenever a control direct effect is identified, this can be identified. And usual property holds. So if there's no mediation, zero treatment effect means zero indirect effect. And if decomposition also works. Okay? Although this total effect is not the usual average treatment effect. It's a total effect in the sense that treatment is 1, and the distribution of M1 is the same what you get under the intervention. Okay? But who gets which value is completely random. Okay? Just the distribution of it. Okay, so I'm going to just skip this, but you can basically identify as long as control direct effect is identifiable. So, yeah, and you can also identify on the experiment. So a lot of people started to look at this quantity. Okay, so the takeaway for the final part is I talked briefly about this post-treatment confounding issues. Control direct effect can be identified under standard exogeneity. Estimation requires marginalization of the post-treatment confounders. The natural indirect effect, natural direct effect as they are, not identifiable. Okay? But you can sort of do different decomposition and focus on the different aspect of this problem, under cross-forward independence. And I also briefly talked about these alternative estimates that some people started to look at, this interventional direct and indirect effects. And this is basically thinking about interventional distribution on mediator. I do think in a public policy point of view, sometimes the interventional distribution is kind of interesting. Instead of saying, okay, you get this, you get that, but you could say, okay, what if the different groups, we equalize, say, income distribution, or we equalize educational attainment at the group level, population level. So that's something that I think we can be a little bit more creative to discuss this. Okay. Okay, so just to briefly conclude, so study of causal mechanism is essential, but quite challenging as you saw. I think triangulation of evidence is necessary. So I've tried to introduce you to some of these different quantities, depending on study design and the substantive interest, and different identification strategies, and different statistical methodologies. So there's a ton out there, and I put in the slides some of the references. There's a review article, there's sort of a couple monographs, and there's some statistical software for those of you interested. So I'll stop here, and thank you very much.
All right, everyone, I think we are going to get started for the second part. So I'm going to talk about a problem that's complementary to what Kosuke discussed. In this case, different objective, but as you'll see, closely related methods, closely related DAGs. Here I'm going to be focused on how we can identify treatment effects on primary outcomes using mediators. So rather than trying to identify the mediating effects themselves, using mediators in a sense as a tool to predict longer-term treatment effects. So in particular, I'm going to focus on 3 different methods that formalize when and how we can use various types of proxy variables to predict treatment effects on a primary outcome of interest that we don't observe directly. So the first setup that I'll talk about is the surrogates literature, which has a long tradition in biostatistics, very well-developed literature. I think has a lot of relevance to economics applications, as we'll discuss in a second, where fundamentally our goal is going to be to predict treatment effects on long-term outcomes using intermediate outcomes, using mediators. The second case I'm going to talk about is what are called remotely sensed variables, where we're interested in predicting outcomes using post-treatment proxies. So not things that are observed along the way in the causal chain to the final outcome of interest, but things that may be observed afterward. For instance, satellite images that are indirect measures of income or something that we're directly interested in. And then the final method I'll talk about is more nascent, thinking about using these intermediate outcomes not as surrogates or as predictors, but rather using them to correct for selection in cases where we think the surrogacy assumptions that we're going to go into in some detail in a couple of minutes don't hold. So all of these methods are closely related to each other. They're all trying to use proxy variables and intermediate outcomes in some way to get at these underlying treatment effects with different data configurations, different underlying assumptions. So let me start with the case of surrogates. So to fix ideas, let's think about the following example. Suppose I've got a job training program. That's the treatment T. And I'm interested in ultimately in its impacts on people's lifetime earnings. So that's going to take, in principle, a long time to observe. You have to follow people over their entire lifetimes. You have to understand their entire career trajectories. Would take decades to measure directly. So an intuitive, very widely used heuristic to get at this is to instead use short-term proxies to predict these long-term outcomes. So what's the logic here? If I see that job training has a positive impact on earnings 1 year after the program, and I see in some other historical data set that earnings are highly serially correlated. So if I tell you your earnings when you're 30 years old, it's highly predictive of earnings over your lifetime in the cross-section, then maybe I can extrapolate from that 1 year earnings impact to the lifetime earnings impact, essentially by multiplying the short-term treatment effect by the correlation between 1 year earnings and lifetime earnings. It seems like a very intuitive way to think about it. This kind of technique is applied all the time in economics and other literatures. Essentially, you can think about what I'm going to show in the next few slides as a formalization of the assumptions under which that approach makes sense, and then thinking carefully about what we might do when those assumptions don't hold. Okay, so to formalize the structure here, let's again use these DAGs in the same way that Kosuke did, where I'm going to talk about settings with 2 different data sets. First, there's an experimental data set where I'm going to have an indicator that denotes which sample we're in. So that's GI here, the group. So here I'm thinking about GI equals E, the observations in the experimental sample, say a job training experiment in this context, where I have a treatment T on the left, I have an intermediate outcome, say earnings 1 year later, that may be used as a surrogate S. And then there's an ultimate earnings outcome that I'm interested in, the primary outcome of interest, which I denote by an open circle. That's the missing data problem that we're trying to solve. We're trying to estimate the effect of T on Y, but we don't see Y in our experimental data. Now we also have another data set, a separate sample, GI equals O. These are two mutually exclusive samples, where in this data set, I don't observe job training. So I just have observational data, say, from tax records on people's earnings. But what I do see are the surrogate S and the long-term outcome, right? So I have panel data on earnings. I can see earnings at any given point in time. I can see lifetime earnings. And so essentially, the question I want to ask is there a way to combine these data sets in order to estimate the effect of T on Y? And the intuitive way that you might think about doing it, the heuristic that I just laid out earlier, is estimate the effect of treatment on S in the experimental data, get some estimate, and essentially scale that up by the relationship between Y and S estimated in the observational data. And so what we want to think about is, when does that approach make sense? Now, before I describe formally what the assumptions are under which that estimator is consistent, let me just make a connection that I think will be useful to economists. Kosuke also mentioned instrumental variables. Think here as well, it's maybe useful to just think about the parallels. So in the case of IV, you think about an instrument that affects an endogenous variable that then affects an outcome of interest. Here, one way that you might think about the setup is that in IV, typically we're able to estimate the reduced form effect, and we're able to estimate a first stage effect. And then we think about assumptions under which, say, taking the ratio of those two things identifies a second stage effect that we're interested in. Here, the structure is a variant of that, where we're interested in estimating, in some sense, the reduced form effect, the effect of T on Y, but we're not able to do that directly. In some sense, we're able to estimate the first stage, the effect of T on S, and the second stage, the effect of S on Y. And so in IV, we think about a division, two-stage least squares as a natural way to get the second stage relationship of interest. Here we're going to essentially multiply the first stage and the second stage effect. So when does that make sense is essentially the problem that we're after. And you're going to see it's not formally equivalent, but you're going to see parallels in the assumptions that underlie the surrogacy approach and the types of assumptions you see in an instrumental variables context, things like exclusion restrictions, assumptions that parallel external validity assumptions, and so on. Okay, so hopefully that can keep that in the back of your mind as I now describe more formally what the assumptions are needed for the surrogacy approach to work. So the first assumption is completely straightforward. It's the starting point for any of this. We're going to assume we have an unconfounded experiment where treatment is orthogonal to potential outcomes, both the short-term potential outcome and the long-term potential outcome. Now I'm going to call this an experimental sample where that unconfoundedness assumption holds. In practice, it doesn't actually have to be a true randomized experiment. All you need is that you are confident in unconfoundedness conditional on X's. Maybe you have a quasi-experiment, maybe you have a regression discontinuity. It might be any number of different particular settings. The point is we just need this assumption to hold in the experimental subsample of your data. So that's the first assumption. The second assumption is a comparability assumption. So if you think about it intuitively, we are going to take a relationship estimated in the observational data and transport it over to the experimental data. In order to be able to do that, there's got to be some connection between those two data sets. In particular, the conditional distribution of Y given S, the long-term outcome given the short-term outcome in the experimental sample, has to be the same as that in the observational sample. Now, I find it useful to think about these assumptions in the context of linear models, where it's very clear what's going on. So take that assumption. Suppose you're in the case where the conditional expectation of Y given S is linear in both samples. So you can write it as alpha plus beta E times S in the experimental sample, alpha O plus beta O times S in the observational sample. What does comparability boil down to in this case? It requires that the slopes are the same in both samples, right? And it's intuitive that you would need that sort of assumption. You're going to be able to estimate beta O, and then you're going to take that over to the experimental sample to do an extrapolation. Obviously, you need that those slopes are the same in the two samples to be able to do that extrapolation. The third assumption, which is key, is surrogacy, what in this literature is just termed the surrogacy assumption. And that is that treatment has no effect on the long-term outcome Y once we control for the intermediate outcome. So treatment has to be independent of Y, conditional on S in terms of realized outcomes. Put differently, surrogacy has to be, the surrogate has to be the only path through which treatment affects the long-term outcome. You can see now a parallel to an exclusion restriction in the context of IV. It is useful, I think, when thinking about these assumptions to think about the context in which they are violated. So in this context, what are we ruling out? If we go back to the DAGs that we started out with, what we're ruling out, most obviously, is a direct path from treatment to lifetime earnings. So if there was some job training program that had no effect on your earnings 1 year later, but put you on a better trajectory thereafter, of course it would be problematic to use earnings 1 year later as a surrogate for lifetime earnings. So that's an obvious way in which this assumption might be violated. But there are also more subtle ways in which you can get this kind of violation. And these are discussed in detail in a large biostatistics literature. I would refer you to this paper by Vanderweel in 2013 that describes some of the many different ways in which this assumption, surrogacy assumption, can be violated. Let me give you one other example that effectively is going to create this kind of violation. So suppose you have a confounder, an unobserved confounder, that both affects the short-term outcome and the long-term outcome. That also is going to create a problem and effectively violate this assumption. How can you think about that intuitively? Suppose all of these variables are positively correlated. Then if you've got a higher level of treatment at a fixed level of the surrogate, S, that has to mean that the unobserved confounder U took on a lower realization. That's how you ended up at the same level of S. If S is T plus U, if T is higher, then U has to be lower in order for S to be at a fixed level. And if U is also affecting Y, that means that whenever T is high, U is lower and Y is also lower. So now you've got basically a pathway that's connecting T and Y because of this confounder that's affecting the short-term and the long-term outcome, violating this assumption. So you can't have that either. So this is a strong assumption. It's the point I'm trying to make here. But as I'll argue later, in I think some empirical applications at least, it is a plausible way to proceed. But precisely speaking, in order to apply the surrogacy approach, we need this condition. Okay. So it's useful, I think, at this point, before we go to identification under these assumptions, to connect this back to the first part of the lecture. So surrogacy versus mediation, what's the connection between these two things? There's a close link between the methods I'm going to discuss and the types of methods Kosuke was discussing. So in mediation, if you think about what the problem was, it's a different question, but in a similar situation in terms of the causal graph. There, we're allowing the treatment to have a direct effect on the long-term outcome of interest, right? That's the whole point. We're trying to figure out how much of the effect, the overall treatment effect, is coming from the direct effect versus the indirect effect. And we observe all three things in our experimental data, and we're trying to do a decomposition of how much is coming from the direct effect versus going through the mediator. In the case of surrogacy, we're essentially assuming, as I just showed a second ago, that there is no direct effect. And then once we do that, exactly along the lines of what Kosuke described, it follows that the indirect effect equals the total effect in this context. We don't observe YI in the experimental sample. We're going to exploit the fact that the indirect effect equals the total effect, use the observational data to predict the link between Y and S, and then extrapolate to find the treatment effect on Y. So these things are closely related in terms of the structure of the data, but different sets of data are observed, and we're making different assumptions with different estimates in mind. Okay, so those are the assumptions we're going to need to apply the surrogate approach with a single surrogate. Now, my view is that in many social science applications, it's very unlikely that you're going to have a single mediator that entirely captures the causal pathway from any given treatment to an outcome. So a lot of this literature, I think it originated in biostatistics for good reason. In the biological context, perhaps it's plausible that you have a treatment through a particular biological pathway, say it reduces your cholesterol or something, that then reduces the chance you have a heart attack, because of a known biological pathway, so we can focus on that one biomarker. I think the social sciences, economics, things are much more complicated than that. There are lots of things going on. It's plausible that there are many different causal pathways, and so I think it's more natural to think that there are perhaps multiple mediators that maybe together satisfy the surrogacy assumption. So coming back to the job training example, maybe it's not plausible that earnings by itself 1 year after the job training program fully captures what's going to happen in your life. But if I also tell you what kind of occupation you were in, what kind of industry you were in 1 year later, maybe that gives us a sense of what the overall trajectory looks like, and perhaps together those things block the pathways from treatment to earnings and together form a valid set of surrogates that satisfy the surrogacy assumption. So say you're in that world. In some recent work we've done with Susan Athey and Hito Imbens and Hyun-Seung Kang, we basically think about how to extend the long surrogate literature to this case with multiple mediators. And the way we do that is really quite straightforward. It's by constructing what we call a surrogate index. So what is the surrogate index? It's the conditional expectation of the long-term outcome, in this case, total lifetime earnings, given the surrogates, which could be, in the example I just gave, various early career indicators, earlier career earnings, and so on, in the observational data. So formally, what is that? We'll call the surrogate index mu as a function of the realized values of these surrogate variables S in the observational sample O. That's the conditional expectation of the long-term outcome given the surrogates in the observational sample. So in a linear model, how can you estimate that? The surrogate index is simply the predicted value from a regression of the long-term outcome on the surrogates. So if you look down here, I just run a regression of the long-term outcome on my various surrogate variables, and then simply take the predicted values using the beta hats that I estimate. That's going to form my surrogate index. Now the key result is that under the 3 assumptions that I stated earlier, and certain regularity conditions, the treatment effect on the surrogate index, which you've estimated in the observational sample, if you now take that over to the experimental sample, right, those predicted values which you can construct, the treatment effect on the surrogate index in the experimental sample is going to be exactly the average treatment effect on the long-term outcome that you are interested in. So the ATE on the long-term outcome of interest Y is the conditional expectation of the surrogate index when you're receiving treatment minus the conditional expectation of the surrogate index when you're in the control group. So this approach is extremely simple to implement. To make that transparent, I'll just talk about the 2 steps in which we can do that. It's literally, essentially 2 lines of Stata code. So you regress the long-term outcome on the surrogates to construct the surrogate index in the observational data. What does that look like? You regress lifetime earnings on various short-term proxies for earnings in your observational sample. And then you simply predict lifetime earnings. Now, importantly, you can do that prediction not just within the observational sample, but in your entire data, right? So I'm imagining a data set where it's got 2 parts. You've got the experimental observations and the observational data, and it's stacked. So when you do this prediction, you see the short-term outcomes in the experimental data, so you can form the prediction in the experimental sample as well. And then in the second step, you simply regress the surrogate index on the treatment indicator, right? So regress that predicted lifetime earnings on treatment, and that is, under the assumptions that I described, going to give you a consistent estimate of the treatment effect that you are after, okay? Now, one thing I'll note, this simple cookbook procedure is going to give you a valid point estimate. It's not going to give you valid standard errors because it's not accounting for the fact that you estimated the surrogate index in the first step. So that second step regression is not going to spit out the right standard errors. That's easy to take account of using a bootstrap. Okay, so let's see how this works in practice and how a practitioner might actually use this method. So to do this, I'm going to talk about an application in the context of job training, the California GAIN job training program, which was implemented in the late 1980s to help welfare recipients find work. So this program was evaluated using randomized trials in 4 different cities in California. And I'm going to focus first on one of those sites, the Riverside site, which prior work has shown had the largest impacts on employment outcomes, perhaps because of its jobs first sort of approach. They focused on getting people into work as opposed to training people and giving them skills up front. So a little bit of a different style of job training program relative to the other 3 sites. So after focusing on the Riverside program, I'm then going to return to the other 3 sites, which we're going to use for out-of-sample validation. And I'm showing you this here, not just to illustrate how the surrogacy method works, but also because I think this approach of out-of-sample validation is extremely important in using any of these techniques. And this is going to be a first illustration of that. Okay, so let's start with the Riverside site, where we're just plotting data from the experiment on employment rates in the control group in orange and the treatment group in green. You can see that at baseline, the employment rates are extremely low. In the control group, less than 20% of people are employed. This is a group of people on welfare. It makes sense you see very low employment rates here. In the treatment group, you can see immediately after the job training program, there's a big surge in employment rates of 10 or 15 percentage points. Employment remains quite high and then gradually reverts back to a lower level. In the control group, employment rates steadily go up over time, sort of a mean reversion pattern coming out of welfare that you would expect to see in any observational data set. So what do you see here? You see a pattern of treatment effects that's varying significantly as time elapses. The average treatment effect over the 9 years, 36 quarters, that were studied here in this earlier paper by Hotz et al. Is a treatment effect of 6.37 percentage points. So the question I want to ask in this context is whether you could have figured out, without waiting for a decade, that this program had a 6.37 percentage point treatment effect. Is there a way that we could have estimated the mean impact over these 9 years more quickly using these short-term employment rates as surrogates? So in order to figure that out, what we're going to do is apply the method that I just described. We're going to construct a surrogate index using data on quarterly employment rates immediately after the job training program. The way we're going to do that is by regressing mean employment over the full 36-quarter period on employment indicators from the first quarter up to some quarter n. So like the first 2 quarters, the first 3 quarters, the first 4 quarters, and so on. We're going to vary n. And then we estimate the treatment effect on the surrogate index based on employment rates up to quarter n, and essentially evaluate how quickly, that is at what n, we start to get treatment effects that look like the long-term treatment effect over 9 years. So obviously, mechanically, if I let n go to 36 quarters, I'm going to match the treatment effect over those 36 quarters. The question is, how much more quickly before 36 can I start to figure this out? All right, so let me show you that with this plot here, where I'm showing in the black line the actual long-term treatment effect of 6.37 percentage points. So let's now see what we get with different surrogate approaches. So suppose we start by just using 1 quarter of data as a surrogate. So I only have information on 1 quarter of employment. I'm trying to predict employment over the next 9 years. So this is like the single surrogate example. You can see this does not work very well. The point estimate you get out of this approach lies outside the 95% confidence interval for the actual estimate. It's not terribly surprising given that there are some quite complicated employment dynamics as you saw in the previous slide. If I just tell you employment 1 quarter out, you're not able to guess how well people will do over the next 9 years. So now let's construct a surrogate index using 2 quarters of data, 3 quarters of data, 4, 5, 6, and so on. And what you see is once you have 6 quarters of data or more than that, you start to get estimates that look very close to what you get with the full 9 years of data. So what this is telling you is n of 6 is enough in this context to get an estimate that matches the ground truth long-term treatment effect. Why is that? Intuitively what's going on is by using 6 quarters of data, you're basically able to see the profile of people's employment rates, see how that relates to longer-term employment outcomes, and if I can estimate the treatment effect on that profile, I'm able to make a pretty good guess about what's going to happen over the full 9 years. Now, it's quite important to actually create the surrogate index by using those 6 quarters separately to capture that profile, as opposed to taking a different approach, maybe a simpler approach that you might have thought of off the shelf, which is just to take the short-run estimate over the quarters that you observe. So suppose you just say, I'm going to take the mean over the first 6 quarters. If you took the mean over the first 6 quarters, you would significantly overshoot the long-term treatment effect, which makes sense if you think about the dynamics that I plotted earlier. The initial treatment effects were much bigger, and then they narrowed over time. And you're not picking that up if you just look at the short-term treatment effect. So that's what the surrogate approach is getting for you. It's forming a prediction of this long-term impact and shrinking the estimates back correctly, taking, essentially accounting for the dynamics. So this is all very nice. And, so when you look at this, you might say, okay, that's great that 6 quarters works in that example, but how on earth do we know that 6 quarters is the right surrogate index to use in some other context? Should I have any confidence in using this in some other setting where I don't actually see the experimental estimate in the long run? So this is where I think validation is so important. Obviously, it's impossible to have intuition on which set of surrogates are going to work in practice. So what we're going to do now is use the 6-quarter surrogate index estimated in Riverside and ask how well it does in predicting heterogeneity in the other sites, which we didn't use in order to construct this 6-quarter estimate and figure out that it seems to work well, right? So this is essentially an out-of-sample validation. Formally, what does that amount to? It amounts to a joint test of the surrogacy and comparability assumptions that I laid out earlier. And so what does that test look like? On the x-axis is the actual treatment effect over 9 years, estimated using the RCT in each of these 4 sites. On the y-axis is the 6-quarter surrogate index prediction. And you can see those two things are pretty well aligned. In particular, you would have been able to figure out 1.5 years later that things are going much better in Riverside than they are in Los Angeles. And you can see, going back to my initial motivation in this lecture, why this is potentially quite useful for policy. Rather than waiting for a decade to figure this out, you might have been able to course correct in LA and do something that looks more like Riverside, which would have benefited lots of people. So that's the idea of being able to use these estimators. Now, I want to be cautious here. Obviously, this is an out-of-sample validation with just 3 observations. Ideally, we'd be doing this with many more observations, but it illustrates, I think, the way in which these kinds of tools can be helpful and the way in which we should be validating them at larger scale to make use of them going forward. Okay, so that's, I think, one approach and a primary benefit of the surrogate index approach. When we don't want to wait for this long-term data, we can use these short-term outcomes to make predictions more quickly. There is a second benefit, which was less obvious to us when doing this work. Susan actually alluded to it for those who were in the morning econometrics session in her discussion, which is that even when you do have the long-term data, there can be a benefit to using the surrogate index. And that benefit is that you can have gains in precision. So even when you do see the full 9 years of data, you may still want to use the surrogate index based on the first 6 quarters because it will reduce noise in your estimate. So why does that happen intuitively? Under the surrogacy assumption that the treatment effect is running only through the surrogates, everything that happens after that point is noise relative to treatment, right? It's just pure noise orthogonal to treatment by assumption. And so it makes sense that you can reduce your standard errors essentially by estimating the treatment effect on the surrogate index instead of directly on the long-term outcome. And indeed, when we implement that in this application, you can see that if you look at the 95% confidence interval for the experimental estimate of the 9-year effect directly shown in the orange versus the 95% confidence interval using the surrogate index, you get a shorter confidence interval, quite significantly, about 30% shorter, because of exactly this logic, that everything that's happening after those first 6 quarters, random stuff happens, people lose their job, they get a better job, et cetera. Under the surrogacy assumption, none of that is related to the initial treatment, so you're essentially filtering out that noise by using the surrogates as the treatment that you're looking at. And so I think that also in practical applications I've found, in many contexts can be quite helpful, especially when you're running short on power, looking at heterogeneity, looking at other types of cuts. As many of us know, directly looking at the long-term outcome, even if you have it, can start to be a stretch. Constructing a surrogate index like this can be helpful. So this is, just a brief sense of this very wide literature on surrogate indices. For those who are interested, you can read much more about work in the space. There's work with alternative data configurations, thinking about treatments that are dynamically adjusted over time. When you have many experiments, essentially like a weak instruments problem, there's work done on efficient estimation in this context. There are a variety of applications that you can look at. I'm going to focus on one of these cases, the Rambachan, Singh, and Viviano paper that was presented this morning, which is a different data configuration, a post-treatment outcome, both because I think it's a very interesting paper that is also very relevant for applied work, and it's also a very useful contrast relative to the data setup that I've just talked about in the context of surrogates that illustrates why thinking carefully about the causal graph in your application is extremely valuable. So this is the case of remotely sensed variables where we're predicting treatment effects using post-treatment outcomes rather than intermediate outcomes. So to motivate this, let me note that there are a number of settings where the variables used as proxies for primary outcomes are not intermediate outcomes along the causal chain, but rather outcomes that are measured after the primary outcome. An example that Rahul and Davide and Ashish gave in their paper is from a development economics paper by Jack et al., where they randomized incentive payments, the TI in this context, to farmers in India to stop burning crop residue from land. So that sort of burning creates a lot of pollution. We want to reduce it, so one approach is to give farmers incentive payments to do that. So the ultimate variable of interest, yi in this context, is whether the land is burned or not. Now, measuring that is complicated. Going around, of course, just asking farmers whether they did it, especially when you're incentivizing them not to do it, that's not a good strategy to collect reliable data. It's also very costly to manually go and survey every single plot. So what they do in this context is instead use satellite imagery, what this literature is called a remotely sensed variable, to predict the ground truth variable we're interested in of burning. So let's think about what the causal graph looks like in this context. So here it's a little bit different structure, basically switched ordering of variables relative to the surrogate case, where we've got the treatment like before. Then we've got the outcome of interest, which we're not seeing, yi in the middle. And then we've got the proxy that we are seeing the satellite image after the outcome, right? So that's switched relative to the surrogate order. And in the observational data, we have a similar structure, but I'm going to assume in this context that you don't see the incentive payments. In their paper, Rahul and Davide and Shesh consider cases where you see it and you can weaken some of the assumptions that I'm describing here, but I'm going to focus for the case of expositional contrast with the surrogates case I just talked about the situation where that treatment data is missing, which I think will be true in a number of applications. So a common intuitive practice in this context, what I would have thought of doing naturally, and I suspect many others, is to essentially use the surrogate approach, right? So what might you think of doing? I predict the primary outcome using this remotely sensed variable R, and then estimate the treatment effect on that predicted outcome. So in this context, what would that amount to? I have this satellite image. I have this ground truth proxy for whether I have burnt land. I predict the land burning using the satellite imagery, create a predicted outcome. Seems totally intuitive. You would then take that predicted outcome, regress that on your treatment, and call that your treatment effect. That's what Jack et al. Do. That's what a number of other papers do. So what Rambachan, Singh, and Viviano show is that that's generally going to yield biased estimates, and we can connect it back to the surrogacy framework that we just talked about, because this is exactly a case where the surrogacy assumption is violated. That is, treatment is directly affecting the outcome of interest, independent of the surrogate, independent of the proxy variable. So let's contrast the DAGs in the two cases. In the remote sensing model, at the top, you've got the treatment, you've got the outcome of interest, and then you've got the predictor variable. In the surrogate model, it's flipped around, and remember, to get identification with the surrogate approach, critically, we required that there was no direct link from TI to YI, the final outcome of interest. But of course, in the remote sensing models, we can see from the upper DAG, that's precisely not the case. There is a direct effect of the treatment on the outcome that is not running through the satellite imagery. And that seems quite natural in this context, right? It's not that the incentive payment to the farmer is directly affecting the satellite image and then having an impact on whether the land is burned. Obviously, it's the other way around. The incentive payment affects whether somebody burns their land, and then you may or may not pick that up with satellite imagery. Okay, so we can see why, something may not work here. The surrogacy assumption is not satisfied. We knew we needed that before for the surrogate approach to work. So it seems plausible there's bias here. So they establish that, and then they go on to show constructively how one can identify the treatment effect on YI in general, in a general setting without parametric restrictions when you have this reverse data structure with post-outcome variables as proxies. So what I'm going to do here is focus on a much simplified version of the general case they consider, again, focusing on a linear case that captures, I think, the essential difference relative to the surrogate model and shows a simple way in which applied researchers can correct their standard estimates to account for this issue. So what are the three key assumptions you need for identification using remotely sensed variables? There's a very parallel structure to the one that I just described with surrogacy. So as before, and as in all the cases we're talking about here, you have to have a valid experiment. That's assumption one. Second, you need something analogous to the comparability assumption that I had before. Again, you're transporting data between these two different samples, so you need stability across the experimental and observational sample. In this context, the key requirement is that the distribution of R, the remotely sensed variable, conditional on the primary outcome, has to be the same in the experimental sample as it is in the observational sample. And then the third assumption, which is analogous to the surrogacy assumption, but sort of in reverse, is that there can't be a direct effect of the treatment on the post-treatment outcome R conditional on Y. So you can't have a direct effect of the incentive payment to the farmer on the satellite image that doesn't come from the farmer burning the land. So that seems like a plausible assumption. There could be violations of that. If the farmer recognizes you're going to use satellite imagery and tries to cover that up in some way, that's the kind of thing that would create a violation. But it seems like a plausible starting point. Okay, so what did these assumptions boil down to in the linear case? So now I'm going to hone in on the linear case and then show how identification works in this context because it's very transparent. So suppose again that the conditional expectation of R given Y is linear in both samples, all right? Then what does the stability assumption require in this context? It requires that those two slopes, dr, dy, are the same in both of these samples. So beta E has to equal beta O. Let's call those slopes just beta, okay? So that's the relationship between Y and R. When I change Y by 1 unit, R changes by beta units in both samples. We're making that assumption that that relationship is the same. Okay, so when you have this linear structure and you make the three assumptions we've just discussed, and you have some additional regularity conditions, overlap, and so on, the treatment effect on the primary outcome of interest is very straightforward. The average treatment effect on Y is simply the conditional expectation of R in the treated condition minus the conditional expectation of R given that you're in the control condition, rescaled by 1 over beta. So in other words, the average treatment effect on Y is just the average treatment effect on the remotely sensed outcome, your satellite image prediction, divided by beta, which is the link between Y and R. All right, so I'll give an applied intuition for this in a second, but again, let me just show the very simple way in which one can implement this estimator in the linear case. So 3 steps to estimate the treatment effect on Y. So when you've got one of these remotely sensed variables, first regress that variable, say the satellite prediction, on treatment in the experimental data. That's what people are already doing. That's what Jack et al. Do in their paper. Second step, regress that remotely sensed variable on the true outcome in the observational data. So you've got this other sample where you've gone and surveyed a subset of plots. You know if the land was burned or not. You also have the satellite image prediction. So regress R on Y in that observational sample. That gives you an estimate of beta. And then simply divide the coefficient of 1, the ATE on R that you estimated in step 1, by the beta in step 2. And that's going to give you a valid estimate of the treatment effect on Y. So let's see how this works in the actual application that they discuss, one of the applications they discuss in the paper. So Jack et al., the first column is the estimate they report in their paper using the satellite prediction. You get an estimate of 0.079, so the way to interpret that is giving farmers these incentive payments, reduced the percentage of plots that were burned by 7.9%, okay? The second column is the correction factor. It says that dRdy, when y goes up by 1 unit, R, the satellite prediction, goes up by only 0.53 units. That's the rescaling factor. And then the corrected estimate is just the ratio of columns 1 and 2, which is 0.148. So in this context, they point out that there's a significant downward bias in the raw estimate using this remotely sensed proxy. Doing this correction matters significantly. So why does that happen intuitively? Like, what's the story behind why you have this bias? So here's one simple way to think about it. The way I think about it is, suppose you've got a satellite that only 53% of the time picks up whether you've actually burnt your land. So like basically half the time it works, half the time it doesn't work. Now the treatment is having an effect on all the plots, right? So if your satellite image is only picking that up half the time, then obviously you need to rescale, you need to double your coefficient to get the true impact of the treatment. That's basically what's going on. And because of the structure where that outcome is observed after the satellite image is observed after the truth, you want to do the rescaling with this regression of the satellite image, the remotely sensed outcome, on the truth, R on Y. That's what gives you the right rescaling factor. So I think this is very useful to know. There are going to be many applications where people can use this technique and the generalization provided in the paper to higher dimensional variables, nonlinear settings, and so forth. I also want to emphasize that you can see how what you want to do here is different from the case where you have intermediate outcomes. And so writing down the DAG and thinking carefully about the causal structure in your problem of interest is quite helpful. Okay, the third and final case I want to talk about before ending with an application of these tools is a situation where we think these strong surrogacy exclusion restriction type assumptions that we had in the first two cases don't hold. So what can we do in those kinds of contexts? So I think there are many applications, I've encountered a number in my own work, where the surrogacy assumptions feel like they might not hold. They don't seem tenable. So one, I think, canonical case, see many folks here who've worked on education problems. A canonical case in education, as you all know, is that test scores are often used as a surrogate for long-term outcomes. So for instance, I might be interested in what the effect of putting people in a small class or a charter school is on long-term outcomes, like their earnings or high school graduation rates. It's very hard to measure that. So often the education literature, a canonical variable that people focus on is test scores in elementary school. But at the same time, researchers in education are well aware that there are many pathways through which early interventions may affect long-term outcomes that don't run through test scores. So there's a lot of literature showing, for instance, that non-cognitive skills or other types of factors may directly affect long-term outcomes, maybe even more so than test scores directly. So that is direct evidence in some sense of a failure of surrogacy. Now, often we can't measure all of those other variables, and so we're left in a tough spot where we want to extrapolate to these long-term impacts, but we're stuck with these short-term measures that don't capture all the relevant causal pathways. So how can we make progress in this kind of situation where the surrogacy assumption fails? So I'm thinking about cases where we have data on intermediate outcomes, So we have data on things along the causal chain, but they don't fully block the causal pathways to the long-term outcome. So this is a relatively nascent area of research. I'm going to talk about one technique that we've developed recently in work, again, with Susan Athey and Hito Imbens, that we call experimental selection correction. I want to emphasize that it's not that we think this is the only method or the best method to address this problem. There's an area of active research. We saw other papers presented this morning that addressed related issues. But this gives you a flavor of the kinds of things one might be able to do to make progress. So the key requirement we're going to impose to make progress here is an informational requirement. We're going to require that you have added information relative to what we had in the surrogate context. In particular, we're going to require that you observe the treatment T alongside the intermediate and the long-term outcomes in the observational data. So remember, in the surrogate case, you just needed to see S and Y in the observational data to estimate the link between S and Y. Here, I'm going to further require that you see treatment in the observational data as well. And what I'm going to show you is when you have that additional information, you can strictly weaken the surrogacy assumptions. You can have a strictly more general estimator in some sense. So now I want to note that this additional information requirement means that we're addressing a different problem here. So the way I think about the goal is doing causal inference when we have observational data on long-term outcomes for interventions that we implemented in the past. So we're often excited to implement some new treatment that we've thought about that's never been tried before. But of course, there are numerous things that people have done in the past, maybe not with a randomized design, not with a clear research design, experimented with smaller versus larger class sizes or changes in teacher quality. There are all kinds of observational things that have happened in historical data. And our goal in some sense with this estimator is to be able to make inferences about the causal effects of those types of interventions when we have experimental data more recently varying those same interventions for which we only see short-term outcomes, okay? So I want to, just to be clear, note that this technique that I'm going to talk about here is not going to be applicable to new interventions for which we don't yet have any long-term outcome data, unlike the surrogate approach. So let me give you a concrete example of the kind of situation we're thinking about, and this is an application we'll discuss in this paper. So as many of you will know, in the education context, there's been a lot of work on the effect of class sizes on later outcomes. In the experimental context, one of the most famous experiments in education is the Tennessee STAR experiment, which randomized kids to small versus large classes in a number of schools in Tennessee. And there are a series of well-known papers going back to work by Alan Kruger and others showing that kids who were randomized to small classes in elementary school in Tennessee STAR had higher test scores. So for instance, if you were in a small class in third grade, you assigned randomly to a small class in third grade. At the end of third grade, you scored about 0.2 standard deviations higher on your end of third grade test scores. So that is known in the experimental data. What is not known, or what much less is known about, is the long-term impacts of these kinds of interventions. So in particular, we and others have done some work linking these types of data to long-term tax records and so on, where you can get this sort of information. But there are other outcomes you might be interested in where no one knows yet what the treatment effect is. One such outcome is high school graduation rates. We don't have an estimate of the effect of being assigned to a small class on high school graduation rates from the STAR experiment because it's very challenging to track kids over long periods of time as they move around, move to different schools, and so on. And so our target parameter in some sense is that green question mark there. What is the effect in the experimental data of being assigned to a small class on high school graduation rates? Now, how are we going to figure that out? We have observational data. We have lots of observational data nowadays where we record information on things like class size. We also record information on things like high school graduation rates. Here I give you an example from New York City where we see that kids in small classes actually have lower test scores on average. So that right there shows you that there's probably some selection going on. And they also graduate at lower rates. Okay, so one way to think about the problem I'm trying to solve is, can I come up with an estimate of the causal effect of class size on high school graduation, fill in that question mark by combining these three cells of information? Under what assumptions can I do that? So to put this in DAG form, this is the kind of data structure we're thinking about, where we've got an experimental data set, where now we want to allow for the possibility that there is a direct effect of treatment on high school graduation rates. So we're not eliminating that direct effect at the top. We also have an observational data set where we want to allow for confounders that may contaminate the relationship between class size, test scores, and high school graduation rates, exactly as we saw in the New York City data. The kids who are placed in smaller classes, perhaps are the ones who have more educational needs. So within a given school, maybe the kids who are in smaller classes are the ones who have lower test scores on average. That would be a story that explains the kind of pattern we just saw in the New York City data. So in order to make progress here, we're again going to make 3 key identification assumptions. They're going to have a similar flavor to the ones we talked about before, but with some important differences. So let me lay them out again. The first assumption is exactly the same as what we've maintained throughout, that we have a valid experiment. So it's like saying, Tennessee Star was actually a valid randomized experiment in this context. The second assumption is essentially a traditional external validity assumption, similar to what we might make in an instrumental variables context. This is saying that the potential outcomes in the experimental sample have the same distribution as the potential outcomes in the observational sample. And again, this is what's going to allow us to move information between these 2 data sets. The third assumption, which is the key new assumption that allows us to make progress and is going to replace the surrogacy type assumptions that we saw before, is what we're calling latent unconfoundedness. What this assumption requires is that the confounds that affect S and Y are exactly the same. So formally, the assumption requires that treatment is orthogonal to the potential long-term outcomes, conditional on the potential short-term outcome. So why does that, in words, correspond to the confounds that affect S and Y being the same? So imagine you had a confounder U that affects both S and Y. Then when I condition on S of T, it's going to essentially capture that confound. And now there's going to be no link between treatment and potential outcomes, potential long-term outcomes. So one thing I'll just note in passing is this assumption. You might note, if you remember the surrogacy slide from some time ago, it looks extremely similar to the surrogate assumption, which was T orthogonal to Y conditional on S. But this is written in terms of potential outcomes, and that was written in terms of realized outcomes. And that difference is quite important. The content of those 2 assumptions is extremely different. In the context of surrogacy, it's requiring that once I tell you the value of the surrogate, I've completely blocked the path between treatment and the long-term outcome. So when I manipulate treatment, there's no longer any effect on the long-term outcome. Here, I'm allowing for the possibility that when I change treatment, holding fixed the surrogate at any given value, there might be a change in the long-term outcome. It's just that there can't be a connection between potential long-term outcomes and treatment. So it can't be that the people who generally have higher graduation rates tend to be placed in smaller classes once I control for their potential test scores, right? So it's a similar looking assumption, but fundamentally different and weaker restriction. So again, I find it helpful when thinking about these assumptions to think through violations, like what are some plausible violations of these assumptions. So let's come back to the DAG that we started out with. This is the setup we're thinking about. What is not allowed? What is not allowed is a situation like this, where just to see what I did, I've taken out the arrow between the unobserved confounder and S. Suppose I have a confounder that only affects treatment and the long-term outcome. I can't have that. So why can't I have that? Basically, what I'm going to do is use the short-term outcome to correct for selection. The way this approach is going to work is that we're going to use the short-term outcome to pick up selection that may also affect the long-term outcome. If there's some variable, say richer parents have their kids in smaller classes and those kids don't have higher test scores, then that short-term variable is not helping me correct for selection. And so then I'm going to be confounded. And that's exactly this kind of situation. So this is one example of the type of thing that's going to be ruled out by the latent unconfoundedness assumption. All right, so now let's think about how identification works. And again, I'm going to focus on the linear case for simplicity. So let's suppose that we have linear models for both the intermediate and the long-term outcomes. Okay, so in the case of the intermediate outcome, it looks like this. You've got test scores that are a function of class size, the treatment, and then some error, which you may think of, for example, as being parental inputs, which affect kids' test scores. Then you've got a similar linear equation for the long-term outcome, y, which in this application I'm going to think of as high school graduation rates. It's also affected by the treatment class size with a coefficient tau y, and then there's some residual variation in y. So the structure we're thinking about here is one where those two error terms are orthogonal to treatment in the experimental sample, but not necessarily in the observational sample. So in this context, the latent unconfoundedness assumption in the linear case effectively requires that we can write the error term in the long-term equation as the sum of two components, the part that projects onto the short-term selection component alpha is, and a residual epsilon I that is orthogonal to treatment. So intuitively, what is that requirement saying? It's saying that once we control for parental inputs, what's driving the short-term variation in test scores, the residual variation in test scores, any remaining variation in graduation rates is independent of class size in the observational sample. So that is, any selection effect that we have in the observational sample would be picked up in test scores as well. That's what the assumption boils down to. So once we make this assumption, it's actually quite straightforward to see how you can then obtain identification through essentially what amounts to a control function approach. So to see that, I find it useful to think in two steps. Suppose you observed alpha is, in this example, the parental input directly. So suppose you actually just saw those parental inputs. Then obviously, under the assumption that we've just made, that the remaining residual variation epsilon I is orthogonal to treatment, conditional on alpha is, you could just run this regression with OLS, regress long-term outcomes on treatment, control for parental inputs, and under the assumption we've just made, you're going to get a consistent estimate of tau y, right? So of course, the problem we have is we don't see alpha is, but we have a simple way to estimate alpha is. And the way that you can see that is just actually by going back one slide. So look at the equation, the structural equation for test scores. Alpha is of course Si minus tau s times Ti. I can estimate tau s because in the experimental data I have randomization and I see the short-term outcome. So I can get an unbiased estimate of tau s, and that means I can form an estimate of Si minus tau s times Ti in the observational data. So I can basically back out the parental inputs in some sense in the observational data because I know what the true treatment effect is that I've estimated in the experimental data. And under the assumption of external validity, that tau s is the same in both data sets, so I can carry the tau s over to the observational data and figure out the selection term. And so that's exactly what we're doing here. We infer that selection term by comparing realized scores in the observational sample to predicted scores based on the experimental estimate, where we estimate tau hat s in the experimental data. So in the context of the application I've been talking about here, in New York City, right, remember where we saw the negative association between small class size and test scores? Based on this logic, we can basically infer that there's negative selection into small classes in New York City, and we can infer the magnitude of that negative selection because we know the treatment effect on short-term test scores should have been plus 0.2 standard deviations, but actually we're seeing like negative 0.1, and so that difference of minus 0.3 has to be selection. That's essentially the way the process is working. And so building on that logic, again, under the three assumptions that I've laid out and some regularity conditions, we can identify the treatment effect on the long-term outcome. That is the conditional expectation of y in the treatment group, controlling for that short-term selection term, minus the conditional expectation of the long-term outcome in the control group, controlling for that same short-term selection. in 3 straightforward steps, right? So you essentially want to identify that difference in conditional expectations. So how do we do that? First, we regress test scores on treatment in the experimental sample to estimate the short-term treatment effect of interest. Then we construct residuals of S in the observational sample based on the predicted values, where again, let me emphasize, you've got the stacked data set, so when you do that prediction, you're carrying the prediction over to the observational sample. Construct the selection effect as the score minus the predicted score based on the experimental data. And then you're simply going to regress the long-term outcome on treatment in the observational sample, controlling for those residuals from step 2, controlling for that selection effect. So you will note that this looks very similar to a control function approach. It's literally what it is. You are estimating a control function, which is that selection term, and including that in this second step estimating equation. And so then when you regress graduation rates on treatment, controlling for that selection term on the short-term outcome, you now get a consistent estimate under the 3 assumptions that we've laid out. So just to stress that connection, again, back to a literature that will be more familiar to folks, in instrumental variable models, Kosuke also mentioned this, we can identify by controlling for the first stage residuals, which capture the endogenous variation due to selection, in the second stage estimating equation. Here, we're basically doing the same thing, but we're controlling for the difference between the observed short-term outcome and the prediction based on the experimental estimate, which again captures variation due to selection. Another connection that you might see, this is why we're calling this experimental selection correction, is a connection to traditional selection correction methods that are based on parametric assumptions and certain exclusion restrictions. So if you think back to the original Heckman, include the inverse Mills ratio in your estimating equation. It's based on a certain parametric model to correct for selection. Same kind of idea here, except you're estimating the selection correction based on an experimental of the estimate of the treatment effect on the short-term outcome. So let me again show you how this works in the data and how a practitioner might use these types of techniques. So let's take the case that I laid out earlier of observational data from New York City public schools with information on 3rd grade class size, subsequent test scores, and high school graduation rates, which have been used in various prior studies. And then we're going to combine that with experimental data from Tennessee Star, which randomly assigned 12,000 kids to small versus large classrooms. And as I noted earlier, there are many papers on the short-term impacts on STAR, but much less known on the longer-term impacts, in particular on the impacts on high school graduation. So let's look at what we see in the data in the context of this figure. So on the y-axis here, in this first dot, is the estimated treatment effect that I showed you before of plus 0.2 standard deviations in the STAR sample. That's the experimental treatment effect on the 3rd grade test score, which I'm going to take as the intermediate outcome, okay, S. So now let's do the same thing in New York City. In the observational data, we got a negative estimate of about minus 0.12, what we saw before. So now let's implement the experimental selection correction on this short-term outcome. Mechanically, you will get an estimate that exactly matches the estimate in the experimental data because you have constructed the correction in order to match that essentially. So now we could then take this and apply it to estimate treatment effects on long-term outcomes. Now this is again a case where I would emphasize, as a practitioner, if you just showed me this and said, now I'm going to use this to estimate treatment effects on long-term outcomes, I would not have any confidence that you actually are getting the correction right. Like, how do we know that this is actually going to correct for selection and later outcomes? So this is again a case where I find having a holdout sample and doing validation quite useful. And so in this context, it's very natural to look at later test scores where in the experimental data, again, the treatment here is being randomized to a small 3rd grade class, but now we are looking, as Alan Kruger did, at the effects on test scores in 4th grade, 5th grade, 6th grade, and so on. And the education folks will recognize a familiar pattern of fade out where you see smaller test score impacts in later grades from that initial treatment. And so one way to validate the experimental selection correction estimator is to ask, we're doing the experimental selection correction only with the third grade test score. We haven't touched the later test scores. Do we match this profile of effects? And in fact, you can see you do exactly match this profile of effects. You end up finding with the experimental selection correction a pattern of fade out that very closely mirrors what you actually see in the experimental data, which I find reassuring. In contrast, if you continue with the observational data where you didn't do any kind of selection correction, you're just way off, wrong signed throughout. So now let's come to the outcome we were actually interested in, high school graduation. If I look at the observational data, as I showed you earlier, you get a wrong sign negative estimate. If you now correct for selection using this intermediate outcome, you end up getting a positive estimate. We estimate that being assigned to a small third grade class increases your probability of graduating high school by 0.7 percentage points. An estimate we would not have been able to obtain just from the experimental data, nor just the observational data, but when we combine the two under this particular set of assumptions and try to validate those, perhaps is a plausible estimate of what these long-term impacts are. Let me make one final point in this context. So I've focused here on selection correction using this particular technique, adjusting for selection on unobservables. You might ask, well, what if I did something much simpler and more standard? What if I just correct for selection by controlling for the observables that I see in the data? We see a number of observables like demographics, school fixed effects, various things that we can control for. When you do that, this is what you get, OLS with the demographic controls. Basically doesn't change the picture at all. So correcting for selection on observables doesn't do anything in this context. And the mirror image of that, if I now control for observables and implement the experimental selection correction estimator, it also doesn't change anything, which makes sense because if you've truly adjusted for selection, it shouldn't matter if you further control for observables. So this is showing you that you're actually able to adjust for selection above and beyond what you can capture with traditional observables, which I think is interesting and suggests there might be some promise in these kinds of approaches. So once again, let me emphasize that we see this very much as a first step in this sort of work. There's a very active literature, a number of papers, including those that were discussed this morning, take this in further directions. You can think about identification with alternative assumptions, which can be alternative statistical assumptions. They can be alternative economic assumptions based on economic models. You can think about partial identification approaches, as in Philip's paper this morning. You can think about more efficient non-parametric estimation approaches, and there are already some early applications of these methods, but I think much more to be done, hopefully an area where we'll see more work. So in the last few minutes, and I know we're up on time essentially here, I want to end by going back to the original application that we started with before Kosuke's section, just kind of tie together the various methods that we've presented today. We've shown you some applications along the way in the context of these econometrics papers, but I want to show you an application from a paper that had nothing to do with econometrics, just to kind of show that these tools can be helpful, for applied questions more broadly. So I'm going to return back to that motivating example I started out with on the determinants of and returns to entrepreneurship. Well, you remember we had this kind of DAG, where there was parent income that might affect various intermediate factors like early labor market experience, startup capital, and ultimately affect whether you start a business or not. And so I want to show how we're going to use the techniques that we talked about in the past couple of hours from the mediation literature, from the surrogacy literature, to make progress on this problem and show you how thinking carefully about those methods actually matters for the conclusions you get in this context, and I suspect a number of other contexts we all work in. So what we're going to do to identify mediating mechanisms is focus on one of the approaches Kosuke described, which is using multiple instruments with multiple mediators to obtain exogenous variation in these mediators and then quantify the role of each mechanism. Now, Kosuke emphasized that things get much more complicated when you have heterogeneous treatment effects and when you have interaction effects. So what I'm going to do is start out with a much simpler case of homogeneous treatment effects and additivity, and then I'll talk about how we might revisit the validity of these assumptions. So I'll give you one quick illustration of how this works. So what I'm going to do essentially is find an instrument for startup capital, and I'm going to use that as a shock to startup capital and then back out how much of the original relationship we saw between parental income and ultimate business founding decisions can be explained by differences in startup capital. So the particular instrument we're going to use, I'll just briefly describe this because that's not the key focus of this methodological lecture, is to make use of the fact that people get large windfalls of cash when firms go public that vary dramatically depending upon their exact hiring order. So if you happen to be employee number 5 versus employee number 10 at Google, it dramatically affects the amount of money you get when the firm goes public. And so here we're just showing that using tax record data on subsequent capital gains realizations by the order, by essentially your pre-IPO wage rank, which corresponds to roughly to the order in which you were hired. And you can see that there's this very nonlinear relationship where if you were within the top 30 employees, there's an incredibly steep slope where if you happen to be hired a little bit earlier, you have a little bit higher wage, you get a much bigger payout when the firm goes public. So now you essentially have differential shocks, and I'll come back in a second to the plausibility of the exclusion restriction here. But you have differential shocks in terms of wealth to people who are hired at different points. And so now what we're going to do is plot the reduced form corresponding to this. What is the probability that you found a business in the next 15 years versus that exact same running variable? And you can see precisely the same pattern. If you happen to be one of the very early employees versus one of the slightly later employees, there's a steep decline in founding rates, and then it becomes much flatter later on. So our exclusion restriction assumption here is that the small differences in the hiring order within the top 30 are orthogonal to potential outcomes of founding a business. You might naturally, question that assumption. Could it be that the initially hired employees are maybe more entrepreneurial, and so they're more likely to start a firm not because they're getting more cash, but because of that latent difference in their propensity to found a business? We do various things in the paper. It's a bit orthogonal to the discussion here to think about that. So for instance, one thing you can do is look at heterogeneity by initial wealth, and you'll see that for people who have a lot of wealth initially, you get a very flat relationship here, which is more consistent with the idea that liquidity matters than that there's just some underlying heterogeneity. You may also note that, if anything, most plausible stories of bias in this context, that the more entrepreneurial people are on the right side of this figure, would lead to an upward bias in the estimate. But what I'm going to note here is when you actually quantify the magnitude of this elasticity, you get an estimate of 0.13% change per $1 million of wealth in the probability of founding a business. That implies, going back to our initial calculations, that figure that I showed at the very beginning of business founding rates by parent income, that only 1.4% of the gap in business founding by parental income can be explained by these differences in wealth. So if anything, if you think there's some upward bias here, if anything, that 1.4% estimate might be too high. And so, while by no means do I want to argue that this is like a perfect instrument, that we don't need to discuss its validity and so on, part of the point I want to make, it's almost helpful for this discussion, is that we can now focus our discussion on familiar issues of whether instruments are valid and how we might evaluate their validity and so on, rather than, when I just endogenously controlled for wealth, it was totally unclear what I was assuming there. I ended up finding that it explains 75% of the original gap. You can see you get a completely different conclusion when you use this instrument. Okay, so what do we think is actually going on? Using a similar technique, which I won't get into the details of here, we use another set of instruments on hiring shocks in labor markets, fluctuations in who's hiring in different periods, as basically a shock to what sector you end up starting out in. Do you end up starting out in a sector where lots of people go on to start firms, like tech, or it turns out in auto repair as opposed to auto manufacturing? People who start out in auto repair, turns out in the data, are much more likely to start businesses down the road. There are certain sectors where people end up becoming entrepreneurs if you get hired into such a sector. We have some random variation in that. That ends up explaining a very large fraction of the initial gaps, something like 30 and 50% across some of the different gaps we look at in entrepreneurship rates. So this turns out to be a much more important factor when we look at this different set of instruments. And so the key implication of the mediation analysis in this context is contrary to what we had concluded initially based on that very simple endogenous control, is that wealth at startup is actually relatively unimportant in explaining gaps compared to the upstream pipeline. For example, the sector in which you start working initially when you come out of college or when you enter the labor market. Now, this conclusion hinges on a couple of key assumptions that Kosuke touched upon in his part of the lecture. And so I want to just talk about how, from a practitioner's perspective, I think about assessing the validity of those assumptions. It critically hinges on the assumption of homogeneous treatment effects. So concretely, you might have two concerns in the context of this application. So first, the samples that we use to estimate these different treatment effects with the mediators are quite different. So, in the context of the IPOs, it's people who are working at firms that go public. In the context of the labor market shocks, it's people who've just entered the labor force. These are two quite different samples. You might worry, like, can we be confident that the treatment effects of wealth would be the same if we looked at people just entering the labor market versus people in the IPO sample and so on? So one thing that we can do is condition on observables, reweight the two samples on observables to look more similar on age, on cohorts, on other demographics. That turns out not to change the estimate significantly. A deeper concern, which is what Kosuke focused on, with those superscript I's, is that there's unobserved heterogeneity. And so the way I think about that in this context is that the local average treatment effects that are estimated by these instruments might differ. So concretely, the people who are in these firms that are going public, you might worry, maybe we see very small wealth effects for them because they already have really good access to capital markets. They're incredibly well connected. They're working at a firm like Google. Maybe money doesn't matter for them. So that's the kind of thing that would, potentially bias this conclusion. So what's the solution one would want to take in that context? You'd want to use instruments that generate different lates. So one example might be to look, say, at lottery winners, completely different population who are getting random shocks of cash. There's a paper by Golosov et al. That essentially does that, looks at the probability of business formation, and shows near zero effects in that context as well. That gives me more confidence in this conclusion that these wealth effects are actually quite small. And so in the context of mediation, what that suggests to us is that it's really these labor market factors that are quite important. I want to make one final point before concluding. So now to tie this back now to the surrogacy applications that we talked about, as I mentioned initially, we're interested not just in whether we can get people to found more businesses, but whether those businesses are successful. What are the marginal returns to the new firms that are created? And so this is where the surrogate index approach proved to be quite useful. So we're not able to see long-term returns for the people in the sample that are being subject to these shocks. So instead, what we do is use a surrogate index to predict returns 8 or 10 years later using indicators shortly after a firm is created, things like revenues, wages, number of employees. And then we're able to compare the predicted returns of marginal entrepreneurs who are induced to enter by these shocks to the returns of the average entrepreneur. And the key finding in this context is that the returns of the marginal entrepreneur are very similar to the returns of the average entrepreneur. And so the punchline, putting all this together in the context of this application, is that this IV-based mediation analysis shows that low-income kids are less likely to start businesses because of a lack of exposure to entrepreneurial industries, not because of a lack of wealth. That, as I've emphasized, is the opposite of the conclusion you get simply by controlling endogenously for wealth. What is going on? I think the sequential ignorability assumption or the conditional exogeneity assumption that you need for that approach to be valid, that the mediator is essentially orthogonal to later outcomes once you control for treatment, fails here because it's quite plausible that wealth is correlated with many other unobservable factors that directly affect entrepreneurship. So that's the sense in which it's a bad control. You're basically over-controlling when you do that regression. The second takeaway is that these surrogate indices reveal that increasing labor market experience induces startups whose returns are similar to the current mean. And so the punchline, thanks to these methods, we're able to say that things like perhaps early career incubator programs or apprenticeship programs, giving people more exposure to entrepreneurship early in their careers may be a key to increasing business formation, successful business formation, rather than just focusing on things like tax credits or loans, capital at the time of startup, a conclusion that we would not have been able to reach without the tools that we've discussed in this lecture. And so in that vein, let me end by talking about, beyond that particular application, some recommendations for empirical practice going forward. The simplest takeaway I hope you'll all get is that writing down the causal graphs underlying your analysis is quite helpful. It helps organize, the set of relationships we have and which way we should be doing estimation. In the context of mediation, I would suggest that we should avoid, as a field, the common practice of simply controlling for endogenous regressors and kind of hoping for the best, unless we have some confidence that this conditionally exogenous mediators assumption holds. There could be cases where that case can be argued, but I think we should make it a practice that we have to argue that case rather than just going back and forth about whether it's okay to include these endogenous controls. My instinct, just from practice, is that in general, you need to find multiple instruments or experiments that vary mediators, exactly as we would now, as standard practice in our field, take a design-based approach and look for instruments or look for experiments when we're identifying treatment effects to begin with. And then from a practical perspective, to deal with a number of the challenging issues that Kosuke raised, which arise when you have interaction effects and when you have heterogeneity. This is just more my practitioner's perspective. My sense has been that starting with the case where you assume additivity and no heterogeneity, and then evaluating robustness by looking at heterogeneity across subgroups, estimating different lates, reweighting, other techniques that we use in other contexts to evaluate these kinds of issues is a practical way to proceed. In the context of predicting long-term outcomes, the second half of this lecture, I think there are, again, different approaches one can take. When you're confident that the intermediate outcomes you're looking at are likely to span the set of causal pathways to later outcomes, it makes sense to use a surrogate index to maximize efficiency. In my experience, in economics context, this tends to work well when you're using early labor market outcomes or firm outcomes to predict later outcomes in that same domain. Perhaps because the economic model is that there's a job ladder, there's certain pathways that you have to follow to achieve later success. And as I noted earlier, even when you do observe the long-term outcome, you might consider using the surrogate index to maximize efficiency when you're looking at subsamples, when you're looking at other cuts where power may be an issue. If surrogacy assumptions are debated, and you observe treatment alongside the outcome in the observational data, you can use other techniques like the experimental selection correction method that I described. In my personal experience, in the context of earlier interventions like early childhood education and so on, there are many causal pathways through which you might have long-term impacts, and these other kinds of techniques, rather than the surrogate approach, may be valuable. And then finally, if you're looking at proxies that are observed post-treatment, using the remote sensing estimators that Rahul, Davide, and Ashish have developed, and other such approaches make sense. The broadest takeaway I'd have for practitioners is that, in general, we should be thinking about how to validate any surrogate or proxy method using direct experimental or quasi-experimental estimates on holdout outcomes, as I illustrated with a couple of examples, both within any given paper you might write, but I would argue more broadly as a field, we would do well to build sort of a surrogate library where we have a general sense of, in this context, using earnings over a few periods tend to work well, and this other context it doesn't. If we had that kind of information, it would enable us to learn a lot more from new interventions that people might conduct. Last point, just some thoughts for the econometricians who are here on issues that might be of interest to investigate further. We've talked about a particular set of tools here. I think there's a lot more to be learned when we may have alternative assumptions and data configuration. So for instance, I talked about one context on how to make progress when surrogacy fails, but that was a case where treatment was observed in the observational data. I think a really important case is where treatment's not observed in the observational data and surrogacy doesn't hold. Are there other things that you can do? I think there are a number of other issues in common applications, measurement error, non-compliance in experiments, and so on, that we haven't addressed here that could be fruitfully incorporated. I focused throughout this talk, and Kosuke did primarily as well, on average treatment effects. Of course, we're interested in many other moments of the distribution, and thinking about how to identify those in this context would be useful. And then I think there are connections between the techniques we've talked about here and traditional econometric methods, literature on data combination, panel data methods. I think developing those further would be very valuable as well. Broadly, I think, as I hope we've illustrated in this lecture today, this is an incredibly valuable area of research, both for science and for applications that can have an impact in the world. So thanks so much. And